And so it ends. We return to Slay the Dragon, Proof of Work Coin, part 3 of 3. We will be discussing Nakamoto Consensus. This is probably the one thing that really does deserve his name. There's 1,000 other things we named after him, but this one really does deserve the name. And so, it's kind of thing that ties together the peer-to-peer architecture and the proof of work mining that we kind of discussed and developed last time. We're at a point now where we can't we have a lot of things in the air, and it seems like they might work, but we don't have a dispute resolution mechanism. And so let's kind of hop into that. So we're at a point now where it looks like this might work, and we're missing one thing. We need a dispute resolution mechanism. When different parts of the network disagree, as they will in a peer-to-peer network, where it takes time to get messages across, sometimes people go offline, this and that, we need a way to resolve disputes. And so that's what Nakamoto Consensus is all about. So, distributed network problems. Distributed networks are really hard. I'm not an expert on this. I intend to become one. But distributed networks are very hard. It's very hard to guarantee kind of data integrity when the constraints of your system are so loose. People go online, offline. It takes a while for the messages to get across, and all that sort of thing. And this is the problem in particular we're dealing with POWCoin. That's where we left off last time. What happens when two nodes mine a block at the same moment and disagree about the chain, right? So Alice mines a block, Bob mines a block. Alice is in China, Bob's in the US. It takes a couple seconds for the block to traverse the network, and for let's say half the network agrees on half the network hears about Alice's block first, half the network hears about Bob's block first. You've now split the network in half, and if you run POWCoin long enough, you'll get there, right? It causes their chain to split. But you might not have actually observed this because you have to run it a while, and the reason is that these things are running in Docker on your computer. It doesn't take very long for a message to get from one Docker container to the other Docker container in normal circumstances. And so, you don't believe me? Well, watch this. So let's hop back over to our terminal. If you ls, you'll see that POW P2P coin 4 is where we left off last time. I just ended up saving that as POW P2P coin.py. And so I'll just kind of show you that POWP. So if you run diff on them, so I didn't update these for the POW P2P coin. Maybe I'll go back and do those. This is the doc string for the doc opt, running the command line, passing command line arguments. Remember, this is how it works. We did that a long time ago. And so all I did was just change the doc opt string. So none of the actual code is different. So I just copied that over. And so next thing we want to do is we're going to be working on POWCoin_1.py. And so that's the way this one's going to work. We're going to start with we're gonna copy over POW P2P-coin. That's like the final version of what we did. We're gonna copy that over, and then we're gonna slowly go and implement this code, then this code, this code, this code, this code. So it's POWCoin_number.py, and eventually POWCoin.py is our final version. And so, just in case you're wondering, like, well, how does Justin do this? And by the way, if you run diff, you're probably not going to get as pretty of an output. And so let me show you what I use, because I think you guys are kind of curious about this. This is ICDiff. You see, it just shows differences between files, but like highlights them with colors and makes it a lot prettier. I think this can be really useful when you're probably when you guys are following along. There are incremental changes between all the different versions of the code. If you just install this, and it's pretty easy, you probably just you just have to, it's actually Python. You just globally install it with pip. Just read the instructions. And in my bash RC, my configuration file, I just set, you guys are curious about this stuff, so I'll just show you. So at the bottom, you'll see there's this line. I just say alias diff equals ICDiff, and then I pass in one command because the the add color, like one of the colors was kind of screwed up, so you don't have to do this. You can just say like diff equals IC diff, and that means every time you type diff into your terminal, it'll use this IC diff instead. So figure you guys are kind of interested in this sort of thing, so I was just going to show you. And so yeah, it's a good way to compare files. And this is what I'm doing when I'm recording the videos. I'll just have I have an external monitor, and I will say POWCoin.py. So this will be like the old version of code, and then this will be the new version of code. Well, let's do it like this. We'll want this 3. So let's say towards the end of the video last time, I'm trying to figure out what we do in the last section. So this is what I'll do. I'll throw this up in a terminal on my external monitor, and I'll just see, okay, well, in the next section of the video, we're going to be just adding a threading.lock, and we're going to stick with lock in 2 places. And so, yeah, that's all I do. And so, yeah, I bet you guys are kind of curious about whether I'm doing this for memory. No, I'm not. I'm doing it this way. So, yeah, so get that out of the way. Let's ls again. And I'm just going to copy POW p2pcoin.py, what we ended up with last time, and I'm going to call it my POWcoin.py. And so, yeah, last time we were doing POW p2pcoin, this time we're doing POWcoin. Every time we just stick my in front of it so it's like your own working version. And we do this to mostly just to escape merge conflicts. If I update some code and I want you guys to, do a git pull, this will avoid that problem. So now we have a my POWcoin, and let's see which one I'm in here. So let's open that. And yes, after the little bit of a diversion there, I'm just here to remind you, I'm going to show you how to cause chain splits like hell. It's a pretty simple thing we have to do. Okay, so we're going to make a small change that will simulate packet loss and network latency. So packet loss is when some messages don't make it across the network, and I think that's kind of like if there's some hardware problem somewhere deep in the network architecture of the internet, some packets won't make it across. And so another thing that happens under realistic circumstances is that every once in a while it takes like 10 seconds or 20 seconds or 1 second to get a message from here to like China or something, or even not closer than that. It's just sometimes it takes a while for a page to load on the internet, for some bytes to be transmitted across the internet. And so we're going to write one small function. It's going to be called disrupt, and all it's going to do is simulate these 2 things: simulate packet loss and latency. I want you to search for TCP handler. I'll just type that much, and if you saw, that's how you search in Vim. If I ever say I'm searching, just look down there. And so so TCP handler. So this is all our networking code, right? So we have our serialization. This function allowed us to read an arbitrary number of bytes out of a socket instead of having to hard code it, right? So now we actually have kind of a protocol for how our data transport works. Prepare message was kind of the other side of that. It would prepend the messages with the length of the message, and so then read message would know how much to read. So yeah, it kind of belongs here. It's a little networking thing. It's weird because this function, if we ever shipped our network, we'd never include this disrupt function, because all it does is like simulates bad stuff, and when we deploy it, the bad stuff will happen on its own, right? And so this is just for like a testing function, but we'll stick it in here with the networking stuff. And so I'm just going to type the whole thing out, and then we'll run it, and you'll see what it does and why we're doing it. Actually, so first I'm going to we'll go like this. So def disrupt. It's going to take 2 arguments, func and args. And so I'll write pass in here just because I'm going to go show you how we will use this. And you can just stick pass. Pass means do nothing. Like basically, it allows you to take some code like this that's incomplete and basically make it so it's not a syntax error. If you leave it like this and save your file, you'll have a syntax error because there's like, it expects an indented line afterwards because that's the Python rule. So disrupt, and then we'll just say pass, and so I'm searching again down in the bottom left. Handle block I'm searching for. And so if you recall, handle block is where we do block propagation, right? Whenever we mine a block, most importantly, we'll call handle block, and at the end of handle block, we will broadcast that block to our peers. And so it's at this point where we want to basically like pretend, we want to simulate some like bad network conditions, some drop packets and some latency. And so what we're going to do is, instead of just calling the method directly, I'm just going to copy it, and we're going to say disrupt of func. So we're actually going to pass in the function itself as an argument to another function. And you can actually do this. So there's a programming technique called functional programming where you do a lot of this type of stuff. You're passing in, you have all these like smallish functions that do specific things, and you'll kind of chain them together. And it's really kind of insane, and I've never found it particularly useful, but some people swear by it. And so you have to Google that, functional programming, if you want a rabbit hole. That's a rabbit hole worse than Bitcoin, I'll just tell you that. So maybe don't Google it. So here, we're going to say disrupt, and then the second argument is just going to be the list of arguments that the function accepts. Right? Pretty simple. So I'm just going to hit Control O here for you Vim people. Control O will go back. Control I will go forward. It like jumps where you've been in the file. So it brings me back to where I was. And so I was thinking I wouldn't teach you guys Vim, but I noticed a lot of you guys are starting to use Vim. So every once in a while, I'll just drop a hint on you, just so you. I see I'm converting some people, and I like that. So I'm just going to type out this function now, and it's going to do two things. So first, if random, so I'll make a little comment. So simulate packet loss, and so this is the first thing we're going to try. So if basically, if we're going to get a random number between 0 and 10, or 0 and 9, it doesn't include 10. And basically, if it's 0, so 1 in every 10 coin flip, so to speak, we're going to just like abort the function. So one way of doing that is just saying if it's not equal to 0, then we'll do what we're planning to do. So we just say func of args. And so the star method will basically turn a list into it'll unpack a list so that you can call a function with it. And so this is like one thing we could do. This would just simulate packet loss. But I'm going to do one more thing. So instead of just calling the function directly here, if you recall, let's go back here. So let's say where did we do this? Yeah, so POWCoin, that's what it was. So blockcoin.py, you don't have to actually, you can just watch along with this. You don't have to go and locate it. If you remember, this was our like EOS, remember our piece of shit EOS that we built? So remember we'd say like, hey, if it's our turn, right? Because in EOS they really like rules, right? They like, they like to share and take turns and stuff like that. If it's our turn, we're going to submit a block in 5 seconds. And so Python is not very good at like saying I want to do something at some point in the future. And so what you have to do is you have to spawn a thread, right? A thread is just like this separate kind of a sort of not a full process. It's like this lightweight kind of process thing that spawns off on your computer and has its like own separate ability to run programs basically. And all it does is it's told, hey, basically do time.sleep for 5 seconds and then call submit block with no empty arguments. And so this is just a reminder. So we're going to do this again. So this is how we're going to simulate latency. We're going to simulate latency doing the same thing. We're going to, instead of saying 5 seconds, we'll give it a random number. And so basically with every message, we'll just give it sort of a random amount of time that will delay before sending that message out. And so this is really nice. Like we have the two, I'll just quit out of this. And so I'll make a comment here. Simulate network latency, and then we'll say threading.timer. Random.random will just give us a random number between 0 and 1. So at the worst, it'll take a minute or a second for to fire off a message. At the best case, it'll happen instantly. And so then func and then args dot start. This is like just a syntax for starting threads. So you see, like with threading, we actually do something similar, right? This is kind of functional programming. It looks like functional programming, right? You pass around a function and the arguments to that function sort of it's a similar idea, right? Like so you've actually seen this before, but yeah. So instead of calling it this way, just like a normal function, we're going to call it this way by putting it in a thread and basically having the thread sleep for a rant between 0 and 1 second, and then firing it off. So again, this isn't useful to make our network better. This is useful to kind of like test our network and demonstrate that realistic network conditions will destroy our network. And so yeah, let's just I think so. Yeah, we have it here. Okay, so yeah, I want to delete this line here. All right, so we're no longer doing that. So we have send message. We have the right things. So yeah, this looks pretty good. And so one more thing, just kind of a code quality thing, just to make it a little clearer. I'm just going to pass in as keyword arguments. So the code will work either way, but this is how I have it in the solution file. So I'm just going to stick it here for consistency's sake, so that we have func equals send message, args equal the args. I think that makes it a little more readable, because then you say like, oh, okay, we're passing in a function, because that func means function and args means argument. So it's like a little. I think that putting that in there actually improves the readability of the code quite a lot. And so with that, let's hop over to a separate terminal. And so the first thing we're going to do is, as always, because the goddamn Docker file is never how we want it to be. So actually, I got to go to POWCoin and then check my Docker file. And so here we have what we want, my POWCoin.py. You'll probably have to edit this. This will probably say something different, because we use the same Docker file over and over in all kinds of different circumstances. So oh, look at this. Yeah, so we've actually we don't use these files anymore, but I guess we keep them in there because we did use them in the earlier videos. That's the hard thing about these videos, is there's so much backwards compatibility. Like, I got to make sure any change I make works for any version of the code. And yeah, that's just kind of how this is set up. Maybe someday I'll figure out a better way to do this, but that's how it is now. And so what we can do now is, I think I've got it up in my history here. I actually use this thing called Fuzzy File Finder. You can plug it, you can hook it up into, this just comes built in with the i3, Manjaro i3 thing that I use. And so it's really nice. If you hit Control R and bash, it'll give you this recursive search. But usually the UI is pretty bad for it, and you only see like the top result. And so this one allows you to get many results, and they're kind of sorted by, you can kind of search them, right? So Docker will show you, anything you see on green, it's anything with Docker. And so this is something you can look into, Fuzzy File Finder, FZF. It's a really popular project on GitHub. And so yeah, I just go up and choose this from my history. You want Docker Compose -F, use this one Docker Compose file with like this kind of sparse topology defined. And then up means, run the containers, and build means like rebuild anything in the containers if some code has changed. So here we go, it's copying over you always want to check this, is it copying over the right files? And so this looks good. One node spun up, it couldn't connect to its peers, but there were no errors. And so they're all synced so far. And look at this, all of a sudden. So remember how last time we weren't getting so many chain splits. Look, they're all three. We have a complete chain split, right? And now it gets even worse because they start to think. Actually, that's the another one coming on for initial block download. So yeah, we have at this point we have everyone's split. They're all mining their own things. Everyone's rejecting each other's blocks. And basically, one of these guys has the best chain right now. See, this guy's got the best chain. Node 0 has the best chain. But none of the peers have a way to basically back out of their chain and go forward on Node 0's chain. And so that's what we're going to be doing today. That's what a reorg is. But so this whole kind of diversion was to show you, like, we have this big problem in our code, right? This one little disrupt method, adding in a little latency and a little packet loss, will basically make it so that we simulate two nodes mining a block at the same exact time. And by same time, we meaning within the band of the time it takes to propagate a block across the network, right? So same time is simulated by either mining really quickly, or by making the propagation take forever. And so that's what we're doing. We're basically making block propagation take longer, and so we're simulating more frequent blocks mined at exactly the same moment in kind of network time. And so yeah, as you see, it just like completely destroys our network. And yeah, so this is kind of like the final flaw. There's no way for this guy to say, like, ooh, Node 0 might have a better chain than me. I'm gonna go research it, see if they actually do have a better chain, and if they do, I'm gonna rewind until I find our last shared block, and then play forward on their chain so I can get the best chain, and now my hash power doesn't go to waste, right? Because if you're mining on this and everybody else is mining on that, you're just wasting your hash power. So I'm going to kill this because my CPU is just screaming right now. So yeah, back to the slides here. And so that's our first little thing. So if you just look at, like, what do I have? So diff. I'm just trying to give you a little bit better sense of what these solution files. Sorry, POWP to POWCoin 4. So we already looked at this, but I'm just trying to give you a little better idea of what these solution files look like. And so yeah, this is all it was. It's just this one line. And so that's, if something didn't work, you can check out this POWCoin_1.py. So we had distributed network problems, and so let's look into some how we might solve this. So Satoshi's sort of like genius insight was he's like okay, you want my protocol to resolve these conflicts? Screw it. I'll just say longest chain wins, and you guys figure it out. That's basically what he did. So by saying, like, let's just let the longest chain win, and that, like, the protocol itself isn't going to engage in these sort of disputes about who's got the more valid timestamp. It's just going to say, hey, the longest chain wins. This isn't a dispute. It's more of like a tie, right? If there's sort of like two blocks that half the networks thinks were the most recent ones, like, timestamps are subjective, sort of, and so he just says, well, it's a tie. You're going to punt, and the next block will break the tie, right? So our situation becomes less of a dispute and more of a tie, which will be broken when the next block is mined. And so it's really this, like, clever thing where it's like, so we now have two, like, valid tips to the chain, and so it's like, and if the next blocks, if both chains mine another block instantly afterwards, you'd have two valid chains, both with the tips and the second blocks valid. And so you can have these forks that exist for a few blocks, and it's perfectly, like, within the constraints of the system. And the idea is that since mining is a random process, it becomes far more unlikely for two blocks to be mined at the same time than 1, for 3 blocks than 2, and in the white paper, Satoshi describes 6 blocks basically will never happen unless somebody's got more than 51% of the network, which is an extremely credible malicious attacker. So yeah, that's kind of what he did. So this is Nakamoto consensus, like, let multiple chains live, and so here's the thing: minor financial incentives, e.g., in particular, the Coinbase compensation, right? Miners get paid. Miners get paid to get their blocks into the most popular chain, right? Into the longest, most widely accepted chain. And so since miners get paid to get their blocks into the most widely accepted chain, they want to be hyper vigilant about making sure they're mining on top of the most the chain that's most likely to be the most popular and the longest. So whenever they observe a tiebreaker, even if they're going to lose some Coinbase by adopting that, like if they think everyone else in the network is going to mine behind that, they're going to mine behind it too, because the odds are so long trying to basically extend a chain that might be more favorable to you, but that everyone else thinks is more valid, that you'll lose money doing that. And so your hash power will go to waste. And so this is one of the things that I think you've probably heard before, but maybe you have kind of a hand-wavy understanding. So I'm going to sort of draw it out for you, use my masterful artistic skills in the Google Sheets or the Google Docs applications, and draw you a pie chart. So let's say Bob and Alice mine a block at the same time. They're in different parts of the network, right? Alice is in China, Bob's in the US. And so they mine a block at exactly the same time, and it propagates such that half the network accepts Alice's block, half of the network accepts Bob's block. And so this is what kind of the hash rate of the network will look like at that time. Half the network is mining atop Bob's, and half the network is mining atop Alice's, right? And so this is a chain split, and this is what this will destroy our network currently, POWCoin. This will destroy it because we have no way to resolve this dispute. And so what happens next? There's a tiebreaker block. Let's say it's mined atop Alice's block. And so what will happen is within a couple seconds, like unless Bob can produce another tiebreaker at the same time to sort of extend the race, extend the tie, make the tie like a 2-block tie, unless he can do that, the entire network is going to see that mining atop Alice's chain is more profitable than mining atop Bob's chain. And so they're going to all abandon Bob, and this is the odds Bob faces. Let's just say that Bob has 1/1000th of the hash rate. So Bob has 0.1% of the hash rate, and even if he's got like one Coinbase sitting in here, it's just probably not worth it to continue mining this, right? Because it's like you can do the math on this, and I won't do it here, but like Bob, it's probably better off for Bob to just abandon. Maybe he'll stick with it for like 10 seconds or a minute or or 1 block, but it's probably better for Bob to just like let these Coinbases go, let them become orphans, and just abandon them, because like everyone else went with Alice. And this is the power of incentives, right? Minor incentives, Coinbase compensation. Everybody wants to maximize the chance their block gets in the chain, in the valid chain. So they're just the most. They're as soon as they see a good chain, they're going to adopt it, a better chain than what they've seen previously. And so here's the question, right? So we said Bob needs to abandon his block, right? And Bob needs to join this chain. Well, how can he do that, right? Like, we only have a way to like add to our UTXO set, right? To add to our mempool. Basically, how do we do the reverse of that, right? We want to like, if Bob has a block that like he thought was valid but now needs to basically be removed, how can he remove that from his blockchain and basically undo the effects of adding that to his UTXO set, right? And so the answer is, we'll go over in detail what that is. The answer is called a reorg. This is a chain reorganization. This is like the implementation detail kind of how Nakamoto consensus actually happens in Bitcoin. And so I really like this picture. It's just like it's really pretty. And so like the idea is like, here's Bob right here. Like let's say Bob and Alice are mining this chain over here, right? And then they had a chain split, right? They both mined a block up here, right? And then so Bob is up here mining, and then all of a sudden he sees, well, Alice has gotten like another block up here, and so Alice has the better chain, and it's more profitable for him to basically abandon this track and go and mine Alice's. What he's got to do is basically back out, right? And then go over here. So that's just a little like visual reinforcement of what we're doing. And so, yeah, let's, as a little review before we hop into it, let's just review, like we're talking about how do you reverse block acceptance? Well, let's review what is block acceptance in the first place. So accepting a block means basically three things. And this is, let's just to keep the, remember, this is our update UTXO set method, right? So if you want to see in terms of code what this means, just look at this, right? See, there are 3 blocks in this code, 3 comments. And so this is what I'm talking about in this video. So review, block acceptance. First thing, you gotta destroy UTXOs spent by the transaction inputs, right? So that's here, right? Del, delete, destroy. So all of the, see the out points associated to the TX ins, basically what is being spent, the previous outputs, the UTXOs that are being spent here, we need to go and delete them from our database, right? Because like you can only spend once. So these are being spent, and we're going to destroy what was previously there. And then so next, we're going to say, let's hop over to the slides again. So next we create UTXOs for every transaction output, right? So that's here. We look at we iterate over the TX outs in transaction.tx outs, and we just add them. We add them to our UTXO set, right? We just stick them with a key. The out point's the key, just to make them easier to delete, basically, right? Because that's how we're deleting them up here. You know, we could do a list, but then we're always trying to figure out what the index is, and just a little more. It's just a little easier if you use a key, right? And so yeah, deleting the. Creating the new UTXOs for every output, and then the last one here is removing transactions contained from. Yeah, I shouldn't say contained. The last one here is removing transactions from our mempool, and so that's what you see here. So basically, like, hey, if that transaction's in our mempool, remove it, right? And so that's just I'm just explaining this function in the slide. So. Okay, so I got something special for you guys here. I'm going to put all my skills to use. All of these Google Sheets draw shape skills I've been developing over the course of this video series. Okay, and I'm going to show you kind of how a chain reorganization works. And I'm covering a couple of these things multiple times because it's just super important. And I want you to get it. And the code might be a little confusing. Like, it's the most advanced thing we do, so I want you to be able to refer back to these slides to make things clear. So, you know, fair warning, I'm going to animate the shit out of this. It's going to be pretty dope. So here we are. We're at block number n. We got like n minus 1 blocks there, depending on whether we're indexing from 0 or 1, whatever. So a bunch of blocks behind. We're at block n, right? And so it's like, at this point, let's say everybody basically agrees that this is the tip, right? And so there haven't been any disputes. Everyone's mining on this, right? And let's say, like, you know, block n plus 1 is mined. Blue block, let's just say blue node. Maybe this is Alice down here. I'm not going to do. I don't have names in these. So it's just blue block mines this one, right? And so, but boom, at like the same period of time, or like shortly thereafter, like let's say you hear about this one, and in half a second, right? And this is all. Okay, guys, I got something special for you here. I have put all of my, you know, draw shapes in Google Sheets slideshow skills that I've been developing over the course of this class to use in this one slide. This is my masterpiece, so I want you guys to respect this. Here we are with block N. Everybody agrees this is the tip of the chain. Here are all the blocks previous to it. They're kind of off screen. And so let's say this is like your view of the world, right? Like this is your node, and you're sitting here, you're mining away, and then all of a sudden you hear about a block. Oh, block n plus 1, someone mined it, right? We'll call it blue block. We're going to be making a blue chain, right? And so we color coded it. So you're doing this, and then shortly thereafter, like maybe like half a second or a tenth of a second, you hear about purple n plus 1. So this could be one of those circumstances where, like, basically whoever mined the purple block hadn't heard about this guy yet. They were still mining, and like sort of within network time, 2 blocks were mined at exactly the same time. And so, let's say like it could be the case that people are mining this one, even though you saw this one first, and therefore you thought it was the more valid one. You're keeping this one around because it's like, hey, people might still be mining this one. So what you do is you're basically going to, this is your main chain, and you're going to make a branch. You're going to sort of store this in another data structure somehow, so you can keep track of these ones that are like sort of competing to be on the main chain. And so, another one is mined on blue, and say, oh, cool, okay, I'll add this to my chain. This is the best, we now have this is the only chain that's n+1 or n+2 long. This one's n+1, so this is the best chain we got. And then you're like, oh, boom, well, we got another purple block. We didn't hear about it soon enough. Like if we had heard about it before blue n+2, we'd have to this would now be our main chain. We're like, okay, well, someone's still mining there, so like here you had to create a new branch. And so when we get this, we're like extending a new branch. So you're seeing some of the operations that are going to be required here to implement Nakamoto consensus, right? We need to create branches, and we need to be able to extend branches. And then you're sitting here mining, your node is just sitting there, and la-di-da-di-da, and all of a sudden, boom, block n+3 in purple. This means that we now have a new best chain, right? Purple chain is the longest, n+3 long. Blue chain, our main chain, is n+2 long. And so here we have to do a reorg. We basically have to say, with our main branch, we have to erase what we did here and then go and play forward on this purple chain, making this our best chain. And so in bullet points here, how would we do that? Well, we're going to start from blue block n+2. We're going to undo each block. We're going to do it backwards, right? Because these are the most recently made edits, right? Like when you're in Google Docs or something, when you write a sentence, right? When you hit Control-Z and go backwards and undo what you did, it undoes the most recent thing you did, right? You don't want to undo the first thing you did. That would be really confusing, right? If you write, my name is Justin, if you start hitting Control-Z and undoing, it's going to start with the N in Justin, and then the I, and then the T, and then it's going to go backwards, right? And so that's exactly what we're going to do here. We're going to start with the most recent thing in our main chain. We're going to undo this one, and then we get to our shared, right? Undo meaning the effects to the UTXO database and mempool, right? That was the previous slide. And so we get to our shared, basically the where we forked, and so we agree on the chain before this, and so then from here we can go and update the UTXO database and mempool on all the purple blocks until we reach here, and now we have a new chain, and we'll want to keep this one around just in case, it could be the case that all of a sudden 2 new blue blocks come. Now we've got to do the same thing all over again, right? We have to go backwards on purple and go forwards on blue because it's longer. And so this ain't easy, right? This is freaking complicated. And this is, I'm going to do my best to explain it. Hopefully I succeed. And so let's kind of talk about what this means when we say undo the effects of the blue blocks, of the blocks in our main chain that are sort of no longer, when our main chain is no longer the best chain we see and we have to basically replace it. So TLDR, we just do the opposite of block acceptance, right? So, this is kind of a pain. I got all that. It's the animations. Maybe they're more pain than they're worth, right? So, what I'll do is, so disconnecting the block, TLDR, the exact opposite of block acceptance. So maybe I'll just look over here and just show you. So, remember how we remove UTXOs that were spent. So if we were reversing it, we'd be recreating the UTXOs that were spent, right? So it's basically every time we saw a transaction, if we were kind of trying to reverse this update to the UTXO database, and we would basically add back in the thing we deleted here, right? That makes sense? We would it has been deleted already, and so we're just going to add it back in. Destroying UTXOs that we created for the transaction outputs, right? If let's say this block created an output and now we have to reorg up here, right? When we back out here, any new UTXOs that were created by block n+1 need to be removed from the UTXO database. We need to destroy those because they're no longer valid once we back out. Lastly, we need to add transactions back to the mempool. If you recall, the third thing we do here is we're going to update the mempool, right? And so we remove from the mempool. And so if we're right, because now that transaction is like in our blockchain, in a block in our blockchain, we don't want that in our mempool. That would be a double spend, right? So now what we're going to do is we're going to add it back in, right? So we're just reversing it. So in order to like handle reorgs, we'll basically need to implement a method just like this that just like does the opposite, that reverses it. And so yeah, this is Nakamoto consensus. Basically what you have to do, and so this is Nakamoto consensus. What you have to do in terms of like code implementation that we're going to be adding to our POW P2P coin to make it the real POW coin, slaying the dragon as I call it, because this project has been so difficult to teach. So every time we see a new block, right? So if we look back to our code, our handle block, basically you don't see an if statement here. You notice that? Like there's no if statement in this code. It's every block we get is treated the same way. Now, it's true that like, sometimes, you might fail. There are like kind of hidden if statements here because if you fail block validation or Coinbase validation or transaction validation, these will raise an error, and that will basically save the same purpose of a kind of an if statement as control flow, right? Like that will reject that will basically halt execution. So, but there are no like explicit if statements. There are no like different conditions we have to treat separately. And so what we're going to do is we're going to be rewriting handle block in order to basically handle six different possibilities. The first possibility is the possibility we've been handling all along, which is we attempt to add it to the main chain, right? That's what happened here, right? When if we go all the way back here, when we saw blue n+1, it builds off our main chain and it's longer than anything. It strictly increases the chain. We just add it to our main chain, right? We add it to blocks, here, right? We just call this blocks. And so that's our first case in the Nakamoto consensus in our new handle block logic. And the second case would be creating a branch off the main chain. So remember when we were here, we heard about blue, and then all of a sudden purple came in. Well, this was creating a branch. So this would be that second case. Third case is extending an existing branch, right? When we were, I'll just go back. So when we were here, right, we heard about blue, so we extended our main chain, and then we heard about purple, and so this was already a branch. And so when we heard about purple n+2, we had to extend that branch. And so this is the third case we'll have to handle in our new handle block code. And so three, I make a note at the bottom. 3 is a trick. Actually, I'll cover that at the end. So 4, create a new branch off of an existing branch. I don't show this here, but like, can you imagine if like right here, let's say we were right here, we got this one, and all of a sudden we heard about like yellow n+2 that forked off of purple n+1, right? If we had another fork up here, we actually we want to be able to handle that one too, right? Because yeah, it could happen. There could be 2 mined at exactly the same moment up here too. So we'll want to handle that one. And so that's kind of like a corner case. Like we won't encounter that too much, but we should handle it. And so lastly, we want to reject blocks that we've seen before, right? So if we're sitting here and we hear about n+2 and then we hear about it again, well, we want to reject it the second time because it's like we already seen that block, man. Likewise, if we're here and like if we're here, we have block n+1 and someone tells us about purple n+1 a second time, like we already seen this. We don't need to create another branch or do anything with it. There's nothing we can do, so we'll reject that. And so that's more new logic. And lastly, like, let's say we were here, we had our blue chain, but we hadn't heard of any purple blocks, right? Like, let's say we hadn't heard of purple n+2 or purple n+1, either one of these, and all of a sudden we hear about this purple n+2, right? This purple n plus 2 will have prev ID will be this ID, which we don't know. So if we heard about this, we basically have to be like, oh man, we're out of date. Let's re-enter initial block download just to try to, we'll go tell our peers, hey, this is our chain. Can you give us a better chain? And if you talk to any nodes that have this purple chain, they'll say, yeah, I got purple n plus 1, purple n plus 2, and purple n plus 3. And so, when you hear about a block you can't connect, so to speak, you need to re-enter initial block download. And so yeah, I said we'll handle each one of these separately. But so 3 is the tricky one, right? So 3, extend an existing branch, right? That happens here, right? We're extending a branch, but it also happens here, right? So it's actually like at this moment when we extend this branch, this is exactly when we need to check and check if a reorg needs to happen if we have a new best chain, and to actually do the reorg, right? So this third case is the hard one. I have one more attempt to visually communicate what's going on here, and the idea here is, again, I'm trying to kind of over-teach this. I'm trying to just bash this into your head because it's confusing. It took me a long time to wrap my head around it, which is why it took so long to make the videos. Sorry. And yeah, there's a lot going on here, and if you understand this, you really, I don't think many people understand this much about Bitcoin, like how it actually works. So, like enough that they could actually implement it like you guys are doing. So, and this is the hardest part in my opinion. And so we're gonna go through and kind of play each block forward as we observe them, just like we did earlier in the animated version. And I'm going to kind of describe how the UTXO set changes. And so here we are in our initial state. This is like back here. Alice and Bob both have 100 coins. And then we observe gray N. And gray N pays Alice. Alice pays Bob 10. So Alice's UTXOs go down 10. Bob's go up 10. And the reason why we update the database is because this goes on our main chain. Same thing happens with blue N plus 1, 20. So we go down 20 and up 20, still adds up to 200. We're looking good. So you'll see right afterwards, kind of right here, we say like right after this, we observe purple N plus 1. And so you'll notice that we don't have like a row in the table. That's because when we add to a branch, when we create a branch, when we extend a branch, anything on a branch, we don't update the UTXO database, right? And that makes sense because these two are probably going to have almost the same transactions, right? Because like the mempool usually, like especially in like currently, the mempool is the like blocks are not completely full, so they're probably going to have almost exactly the same block. So like if we went through and updated the UTXO database on these, it's like there'd be conflicts, right? They're not on our main chain. Like this is a different chain. UTXO database only corresponds to this main chain. So we observe purple N plus 1, we hold on to it, but we don't do anything to our UTXO set or our mempool. And so we get blue N plus 2, there's another transaction with 5 in it, so down 5, up 5, we're good. And once again, we observe purple N plus 2. Don't do anything, right? Because it's not going on our main chain. But here we say, okay, we observe purple N plus 3. Reorg begins. We have a new longest chain. And so the first thing we do for a reorg is we remove blue N plus 2. And so you'll see these were our balances prior. And so because blue N plus 2s had a payment of 5 from Alice to Bob, when we reverse that, we increment Alice's balance by 5 and decrement Bob's by 5 because we're reversing this transaction. And actually this transaction, well, I don't communicate this anywhere in the chart, but this goes right back in the mempool. When we remove blue N plus 1, we do the same thing. Remember, this transaction had 20 coins from Alice to Bob, so we reverse that. We send those coins back to Alice, and Bob loses what he once had. And so now we're back to the state of the world we were after gray N. And then so you'll notice gray N is like a shared state. So we actually like don't do anything with gray N. This is like, okay, we're good here. We both agree on this. So we don't need to do anything with this block. Now from here we start playing forward on purple. So let's say purple has 20 from Bob to Alice. We'll bump up Alice 20, move Bob down 20. likewise, 5, 5, and then 10. And so between them, there's 15 coins that move. So Alice's goes down 15, but Alice's goes up 15, Bob's goes down 15. And so here we are, the reorg has ended. And so, these two transactions will be back in our mempool because we're not included in these blocks. We will have, this will be now stored as a branch. This will be our main chain, and our UTXO database looks very different. And so I hope you have a little bit better idea what's going on here. What we're going to do is we're going to start, we're going to go jump to the code, and we're going to basically write out some conditions that that sort of define when we want to handle each one of these. We're going to find a way to spot these 6 different conditions. And then we're going to write code handling them one by one. And if you recall earlier, one time we used unit tests. Unit tests are a piece of code that will test our code and make sure it does what we want it to. So I went through the trouble of writing out a ton of unit tests, big long unit tests that you don't totally have to understand, but that will kind of test our code and make sure that, like, if you have a little typo, this will really help with debugging. You know, if you're on Slack and you're trying to communicate why, like, for some reason your thing just doesn't work. Well, now we have the unit tests. You can run the unit tests, and I'll be able to have a much better guess of what the problem is. So we're going to do that. We're going to have about 6 or 7 unit tests. We're going to go one by one, making it correct for each one of these. And then at the very end, we'll be able to leave in our disrupt method. Remember, we had this disrupt thing where it caused chain splits, which we demonstrated at the beginning of this video. It will no longer cause chain splits once we implement this consensus because we have a way to recover it. We have a dispute resolution mechanism called a reorg. And so, yeah, with that, let's hop over and start writing some code. Okay, we're back in the text editor here, and I'm going to split the screen, and on the left side I'm going to just type the word test into my, so once again I was telling you about this fuzzy file finder. That's actually what this is as well. This fuzzy file finder plugin is like very multi-purpose, and it's just great for finding files in your file system without having to get the name of the file perfectly right. So here are POWCoin _tests. This is what we want. So I wrote a bunch of tests for this, and that's how we're going to go about writing this section of code. Mostly because I think it's the hardest part, and so I didn't want to leave you on your own. And so if all of a sudden it wasn't working in Docker, you had sort of no recourse and no way to communicate what was wrong. With this, I can ask you to run the test and say what happens, and if one of them's failing, then we can go and say, well, what is the error message? Which line is it failing on? And then we get a much better idea of why your code doesn't work, because we have tests that sort of check for correctness. And really, we should probably have this for all the code that we write. But since this is the first time through, I don't want to constrain. The tests are great because they ensure your code is correct, at least in some ways, but there's a cost to them. It's harder to refactor, it's harder to change things. So the first time around, I've kind of tried to avoid tests because this is all going to change, so I don't want to commit to it too heavily. But for certain things like this, I think tests are really nice because they're going to help you get unstuck when you find a bug, get help from me, and stuff like that. So I do a couple different things here. First off, you'll see I import my POWCoin as P. So this is a way of importing and renaming something. And the only reason I'm doing that is because I don't want to... Actually, I don't even need to do that, but I'm going to leave it in just because, what the hell? Now you can do that. And so the reason I do it is I set the P, so P at this point is a module object. It's actually it's sort of think of it as representing a file's worth of code, right? Because my POWCoin is kind of like a file. It's much more generalized than that. So this could be like a whole directory, or this could be like a few different you can do whatever you want. But when you import, you get a module object. And so the module object, if you go over here and we search for POW_target, this is just a global variable defined in the module. And so what you can do when you import it, you can actually change that. You can set it to something different. And so what I want to do is I want to go set it with difficulty bits equal to 2. So, really low. And the reason I want to do that is because I don't want to wait around while my tests run. I want the tests, I want all the mining to be, I want like, 4 hashes and we're done mining. That's what I want. So, and so this is about what, this will approximately get us that. And so yeah, I mean, there's nothing magic about the number 2. I mean, 0, just 2 to the 256 would probably be a smarter. I guess you want it to hash a couple times. So yeah, this is fine. And so I have just a couple of helper methods. The first one basically is a wrapper around prepare simple transaction. This is the one thing this is how, it was a simple way to just like pack together enough UTXOs. You don't remember this one? It's enough to pack together just enough UTXOs in order to send a certain amount to someone else. It's like a simple trivial transaction. And so it's just a wrapper around that goes and fetches the UTXOs for you first, because that's what it took as an argument. And so I don't want to go and change this function now, because again, backwards compatibility, we basically use this function everywhere. So I'm just going to leave it how it was and just make a little wrapper in my test case just to make it easier to say send underscore TX. And that'll just it'll just prepare a transaction. It doesn't like send it over the network. Send TX is probably a bad name. Yeah, probably a bad name, but I'm not going to change it because we got to ship this thing at some point. So I'm just going to leave it in there. But that's just like calls simple transaction. Just prepares a transaction and fetches the UTXOs first. And yeah, so it takes a node as an argument. Because in this one, some of our test cases, we'll have like Bob's node and Alice's node. We'll have multiple nodes simulating a network, sort of. So we'll want like Bob's node to be able to mine a few blocks, and then Alice's node to come along and say try to basically mine independently and fork, create forks and stuff. So next we have mine block. And so all this does is you'll recognize some of this code, right? Prepare Coinbase. Unmined block, mined block. Like think to yourself for a second where you've seen this before. So this code is you're right. It's almost exactly the same as in mine forever. So I'm just taking like the body of the function definition in mine forever. Not the body, the code within the for loop. And so we're removing a little error handling. And because we don't have to deal with interrupts, right? Like this is basically to deal with interrupts. Remember, like if the mining interrupt is observed to be set, we clear it and then return early, and we return none, right? And so over here we can check like, hey, did we get none? And if we did, then we ignore it. But if we got something, meaning a block, we mine a block, then we try to handle it, right? So we're just taking this and making it a little easier to use, in context of a unit test. And so let's just kind of go from the top, and I'll sort of describe what each of these tests do. So, and these will roughly correspond to the those 6 conditions we saw in the spreadsheet or in the PowerPoint. So, for example, here's a test duplicate. So, Bob will mine a couple blocks. So what we have here is we'll have 2 nodes. They'll both mine a Genesis block, and then Bob will mine 1 more block. And the way it works is like this. This is what is being mined on top of. This is what, if you look up in mine block, it has a bunch of parameters, which is a little annoying, but it's actually really convenient. So previous block, this is what we're mining on top of, and this is the mempool. So like prev ID will go in here. Prev block.prev ID will go into the block itself, and then mempool, of course, will go into the transactions on that block. And nonce is just a way, like, if we want 2 people to mine, if we have like 1 person mine a block, we want to make sure the other person will mine a block and get a different result. Just like starting with a different nonce is something I think I use. I might have even deleted that, so you can kind of safely ignore that. But so that's what we get. Then Bob mines a block, And then so what we have is, so within mind block calls handle block, so that'll actually like handle it. And so then what we do is, again, we call handle block by like call it again. And what we're checking is that you can do this with pytest.raises. This just says like I want an exception to happen here, right? I want an error, and that makes sense because our code should error out if we give it a block twice. And so so yeah, that's something we'll want to implement. And then some more stuff. So this one just checks. Then we do another one where if we see a duplicate block that's in a branch, this one just checks if we see if a block is already in a branch, then we should reject it because we don't want 2 copies of a block in the main chain or in a branch. We only need one of anything. So so yeah, then we do test extend chain. So this is really simple. This is what we've done before. Yeah, I mean, we don't really need to do that. That's pretty damn simple. Test fork chain is pretty basic. We have one node, then we mine a Genesis block, we mine another block, and then here what we do is Alice. We basically have we mine another block, but using a different public key. So what we do here is we mine a block, and so we just go and mine a block again. And actually, the way it works right now is when you mining a block again, we'll create a new Coinbase transaction that's separate. And the way we're doing it now, when you create new transactions, the ID is like a randomly generated thing. And this is one of the eyesores in our code. Like I was going to change this. Do you see how we pass it in and we randomly generate it every time? So like this is an eyesore, and I think in like I'm not going to fix it in this video because I feel like this is something that should be better fixed in the next version of the videos, and maybe in like at the end I'll go through and well, at the end of this we're going to try to actually deploy this network, and this is one of the things we can actually fix. But and so I'll just I'm not going to make a video about that. I'll just show you how to improve it, how to fix it. So what will happen is every time we create a Coinbase transaction for a new block, it will be a different ID, and then so the ID of this block will be different. So these will be 2 distinct blocks, even though they were they basically contained the same transactions, right? They had the same parent block and they had the same list of the mempool, which was just like empty list over here. You can kind of see it better up on this line. These 2 empty list. So yeah, these 2 blocks will have separate IDs. They'll be distinct blocks because that's how we remember. That's how we at least maybe we don't have it yet. So we'll have to add a dunder EQ method here to compare them. We'll just compare when we compare blocks. We just check if their IDs are equal. And so yeah, what we do is we do some assertions about what the balances should be. So you can read through that. And then lastly, we check that this mine block here did not add another block to the main chain because it was not longer. It extended off the Genesis block. It did not extend off the tip. It did not extend off of like Bob block. And so we say that the chain should only be 2 long, right? These 2 should be the only 2 blocks in the chain. And then we say there should be at least 1 branch, right? So node.branches is something we haven't seen before. And so yeah, this just checks that when we when we mine a block that extends on a block that is not the tip, when we observe a block that failed to extend the chain, but which we didn't know about previously, we will make a branch for it, basically. I won't clarify any more than that. You'll see. And so we have a few more tests. Maybe I shouldn't. I won't explain them all right here. Maybe I'll go one by one. But you'll see, like for example, extending a fork. Remember, if we have a branch or a fork, and then we add another one to it, it should extend. It should get 1 more. And then, but this is not in the case of a reargs. This does not consider reargs. And then here's one where we test a forking fork. This is the worst test name ever. Test forking fork. A test block forking fork. This is where we, if one of our a block in our, if we have a branch that's like 2 or 3 long, and then one of the earlier blocks, we have another branch off of that, we'll have to handle that separately. And so that's just kind of a lot of code that, not super important. But here's the fun stuff, like test reorg, test successful reorg, and then the really tricky part, test unsuccessful reorg. Basically, if there was a transaction like, so this is a tricky thing. Like, let's say there's a transaction in this block. Let's say there's a transaction in this block that didn't spend a valid UTXO. Actually, you wouldn't be able to know before you reorged whether these transactions do or don't spend valid UTXOs. They might be spending something in here. And like, unless you're going to go and maintain a separate UTXO database for every one of your branches, which would be a goddamn nightmare. Actually, maybe not, but like it's beyond the scope of this class. We wouldn't want to try that here. Without doing that, you really don't know whether the spends in this transaction are valid or not. You can do some validation on them, right? Like you can check, hey, do the inputs equal the outputs in terms of amounts, or is it just like properly formatted? Like, is it just ridiculous, right? You can check if there's just like some things that are obviously wrong, but you can't check everything because you don't know what the state of the UTXO database is in the block before it until you actually rewind and start your reorg and get here. So the tricky thing is when there's a bad transaction in here and you reorg back, forward, and get here and you're like, oops, this is bad. Then what you got to do is you got to like revert your reorg, go back here, forward, and then delete this block. So you basically have to go like back to this state, right? That's tricky. So yeah, that's something we'll test in our unit test here. Let me full screen that. So that's what this test unsuccessful reorg is. And this stuff's a little messy. Like I probably shouldn't be printing and stuff. So yeah, maybe I'll edit these tests a little bit. There's probably a bug in one of them, but it's good enough, and I think it'll help. So yeah, like kind of like good enough tests often help a lot. They don't have to be perfect. And lastly, yeah, you can see there's all kinds of fix-me's in the code. It's I don't feel like making this perfect. I think this is good enough, but eventually, second, third time I teach these things, and the stuff gets really good. Hopefully, I'll do everything perfectly. It's a dream, right? I can dream. And so let's try to run the test. So I'm going to hop over to a terminal. I'm going to clear, and let's see if I have So I'm in POWCoin, right? The subdirectory. I have my virtual environment active because PyTest is something installed in the virtual environment. When you're running Docker, you don't actually have to be in your virtual environment because Docker will, like virtual environments are spun up within each Docker container for each of the 3 nodes we have. And so maybe some of you guys have gotten out of the habit of activating it. And so if you remember, this is like source, then, bin, activate. So when you're in POWCoin, you have to go like ... This is like directory above because the parent directory is where the virtual environment is. So if you're in the base directory, you just go like, you just do it this way. Right, so you just have to go get a path to that activate file. And actually, I showed some of the newer people what this activate file does. Let me just like hop into it really quick. Have you ever noticed how when you leave a virtual environment, you say, like you leave it by calling deactivate? Like actually, in the activate file, a function is defined called deactivate. And this is a shell script. This is not Python. It's like a script that's native to the terminal. And so what it does is it basically undoes everything that the rest of the script does, and then it actually it destroys itself, self-destruct, right? So you can't call deactivate twice, right? So for example, see deactivate, that gets me out of my event, but when I try it again, it's like, I don't know what the hell you're talking about. Isn't that kind of funny? So if I activate again, and now it's defined. So yeah, where was it? So let's just look at this again. Basically, the important thing here, all that this does is it says, it has a hard-coded thing like where in my file system is this venv folder. It's home, Justin, dev, digital, like for development. That's where I put all my code. Digital cache / venv. And then what it does is it just sticks that on the front of your path. So in shell scripts, the way they do a list is it's like a string, but the values are colon separated, right? And dollar is how you call a variable. So $path is like your current path, and then that virtual environment folder, this folder, and then /bin is basically where all of the special code, where all the special stuff that is involved in the virtual environment lives. And all it does is it just sticks that on front of your path. And so I deactivated my virtual environment, and then I'm just going to say echo $path. I'm just going to have it tell me what's in the path. And it just has some stuff. Like this is some of the stuff I was goofing around with for the hardware wallet portion of the course. Here's like, for Rust, this is where the Rust code goes. There's the fuzzy file finder. That's where it sticks like its cache of the files on my system. And there's some of these other things that go on to your path. And so like user bin, user local bin, these are where like, your system will usually install stuff. And so what happens is when we do source venv bin activate and then echo path again, this is all it does is it just sticks this value in the front of the path. And so if we want to, like, let's ls that folder and see what's in there. And so you see, like, oh, there's a Python in there, right? So what happens when we call that? We just like execute that file. Well, that just drops us in Python. And then if we say import ECDSA, it knows about ECDSA, right? If you're outside of the, like, let me just deactivate the virtual environment to convince you even more. I'm in here and I can say import ECDSA. That's magical, right? I'm not in my virtual environment, yet I can import ECDSA. That's because I just called this Python. When you're in your virtual environment, that's all it does. It just runs this file because that's on the front of your path. And whenever you enter something into the terminal, that's all it does. It just looks on your path and finds the first one that matches, right? So if you put like I showed, if you put, this is an exercise to the reader, okay? Stick a file in here in this directory for you that is called like foo, and in foo, actually, well, screw it, let's just do it. So we'll just call it foo, and then inside we'll say echo foo, because echo in bash will just like print it out. And so if we just type, if we source our virtual environment and then type foo, oh, it won't let us. So you can say, you can make it executable, chmod a+x. That's just, or I think you can just do +x. And then if you type foo in your terminal, it'll actually find that file in this virtual environment folder, and it'll run it, and it'll print out foo, right? Because if you remember, that's all it does. It just says echo foo, echo in a terminal just prints out the whatever comes after it. And so this is like, I don't know. You've been dealing with these virtual environments a little bit, and this is like what's going on behind the scenes. And I described this in office hours to a couple people, and they seemed really interested in it. And so I thought I'd share a little bit more. That's just like a 4-minute detour. So hopefully that is interesting. And so when you're in your virtual environment and you type PyTest, think for a second. Where is it finding that file? Right here. It's in that folder. So that's why you can just go and test PyTest. So if you're in the virtual environment, PyTest will do something. If you're outside of it, PyTest is like, I don't know what you're talking about. Isn't that kind of interesting? So yeah, this is what's going on with the virtual environment. All it does is basically hack this path variable and stick stuff on the front of it so that it can find, it finds these, and it doesn't find, like I have a Python that's in like user local bin, I think. It's in like one of these, user local bin, I think. So when I'm outside of my virtual environment, I can say which Python and say yeah, user bin Python. And so that's, user bin is here on my virtual env, or in my path variable, right? And so when we activate the virtual environment, it never searches this far to find a Python or a PyTest or anything. It finds it here first because this is on the front of the list. So yeah, I mean, that's apropos of nothing. You don't need to remember it, but I think it's a little bit of color and context for what a virtual env is and why we use it. Like we can have all this special code that is different, and we only have to run this when we're dealing with our project, and none of these things have to ever deal with the rest of our system, to pollute the rest of our system. So now that we have that out of the way, let's get back into our virtual environment. So we got the venv on the side here, and then let's try to run the PyTest. So for that, you say PyTest, and then POWCoin _ tests.py. That's all you got to do. And so you'll find that to begin with, none of this works. It all has the same error. It says my Genesis block takes one positional argument. And so this is just a little thing we do so we want to be able to pass a node into my Genesis block. If I hop over here, this is what it's doing. It's mining on the global node. And so in our test, you see sometimes we'll have two different nodes. And we'll want to basically say which node we're dealing with when we call mine Genesis block, right? So like, for example, so yeah, we have two different nodes. We call mine Genesis block here with node, the main node, and then we call it here again with Alice node. So we want this flexibility to be able to tell it which node to use, and basically what that means is like it goes into that node's blockchain and it updates that node's UTXO set. And so yeah, that's just like a little thing we're going to change. So we're going to say like don't use the global node, so delete that first line, and then just pass node in as an argument here. And so when we do that, we're going to first want to see everywhere we use mine Genesis block in our main code here, and that's just in the main function at the bottom, right? When we call serve, when we actually run it, we just want to pass in node, right? This node right here. So hopefully that's not too, we're just changing the calling conventions to make it a little easier to test. And this is actually something when you do, some of you are newer to programming, when you do like real programming where you're going to write a service that is in use by a lot of people, one of the things one of the big considerations is every piece of code you test, you want to be able to test it. And if you have any sort of a regression, if something fails, if a bug is introduced, you want your tests ideally to catch that bug, and that gives you a lot more confidence to refactor, to change how things work, because you know you can catch your bugs when you introduce them. And every programmer introduces bugs. Like the best programmers even are introducing bugs constantly. It's just a fact of the programming trade. And so one last thing we want to do, I'm just going to hop back up to mine Genesis block. If you see over here, I think in some places we actually will, like we want to be able to return that block. So we're just going to say return mined block. Whatever we get here that like has the proper nonce on it, we're just going to say return that. Because sometimes over here, for some of the tests, I decided it'd be nice to just have the Genesis block. And if we look, yeah, so here's an example. Like, I want to be able to grab that and call it B0 because later on, after we do a reorg, yeah, so that's like before a reorg, and then this is like, yeah, here, this is like right after a reorg. So it's like, hey, I have 2 of Bob's blocks and I have 2 of Alice's blocks. So yeah, you don't have to totally get this, but like, I want to be able to say like this is Bob's Genesis block. It's just a little easier if I can, if mine Genesis block will return whatever it mined. So yeah, just add a little return there. So let's hop back over to the tests and run them again. Okay, let's see what we got. So this is probably, we have a number of little errors here. And so this is the one we're going to tackle first, and it takes a little bit of skill to be able to read this output. It helps to like look for the names here. The first thing we're going to try to do is to get this test extend chain to pass, because that's like where we were previously. And so the test is failing because we're saying assert node.branches is equal to the empty list, right? Assert that when in the act of just extending the chain, no branches were introduced, right? Because we're just extending the chain, we don't need branches. We don't need to create any branches. It should be the empty list. And the problem is that our node class actually does not have a branches attribute yet. So let's hop over here and add that. So class node, search for that. And then right below blocks, I'm just going to say self.branches equal the empty list. So this is going to contain, basically, this is going to contain full branches that are kind of competing with our main chain. So like for every one of these, the first element will be a block with prev ID equal to something that's in the chain. That's gonna be our constraint here. Is like we always want our branch to be able to point back to it'll build directly off something that was in the blocks itself. And this is, I think the way we do, I think there are some little bugs probably here, because what actually can happen is, you can introduce one where like the prev ID is in the chain, but if you reorg, then all of a sudden that prev ID is not in the chain anymore. So if you follow me there, you might be able to spot some bugs, and if you do, let me know, because that'll kind of test your knowledge here. So where you can have a branch that's valid, and all of a sudden after a reorg, that branch all of a sudden doesn't point at anything valid anymore. So yeah, that I don't know if I bet you could get the program to crash if you gave it the right set of blocks. So maybe if you wanna write a unit test for that and see if you can get like some really bad, or just write a little script that feeds it the right blocks, you could probably get it to crash, honestly. So and yeah, this is like one of the things I want to do when we get into the section of the course where we actually try to start to deploy this thing. It might take us like a couple weeks or a month to actually get a deployed version of it, but I think it'd be really fun to deploy it and actually run it as a network and like practice trying to crash each other's nodes and steal each other's money, and do like mining attacks. So like maybe a few of us like don't mine for a period, like maybe our mining period's a day, like none of us mine for a day, and then we like mine like hell for another day to like screw up the difficulty, stuff like that. I think that'll be really fun, but not to get ahead of ourselves. So all we have to do is just add in self.branches here, and hopefully hopefully this test will now pass. And so one thing we can do to run just this test is we can say, we can at the end here after the file name, but with no spaces, we can put : and then test name. And you see that? So now all of a sudden, it doesn't give me a whole thing. It just it says collected one item, and there's no error. And down here it says one test passed. So that test passed. If you don't believe me, we can comment that line out and then try it again, and then we get the same error we were getting before. So this is just a little something to like, if you're overwhelmed with the amount of output you're getting, this syntax is a way to just call this one unit test, and I think it's kind of nice. So let's hop back over here and uncomment what we had. Now we should be back to a passing test. And so the next thing we're going to attack here is test forks chain. So that was the other one of these two methods these two tests I described, and this is just where we get a block. This is where we get two separate blocks that mine on top of something that was in the chain. So we get a first one, and that goes in the regular chain. We get a second one, right? They're both mining off the Genesis block. See, that's what they're mining off of. And so they should both go at, so the second one shouldn't go in the main chain. It should go in a branch. And so that this self.branches we just defined, we're trying to figure out how to write to that, how to add stuff to it. And so this is what we're gonna want to add. And so I'm gonna walk you through this, and we're gonna do some refactors along the way. And so we're gonna start sort of like outlining how this will change. And so if you recall this section of the slides, remember we had these like 6 cases. So we're going to actually start defining some variables so that we can sort of pick these off and identify them. So let's start with extend main chain and create a branch off new chain. We're going to create variables that indicate whether either one of these cases is what we're dealing with. So let's hop back over here. And so I'm just going to like make some lines here. Like we're going to be repurposing a lot of this code, but I'm just going to make some empty lines just to sort of like logically separate it from the new stuff. And so the first thing we're going to want to do is we're going to create, I'll just say, conditions. Like I'll comment conditions. These are the different conditions that govern how we're going to do how we're going to handle this block, whether it's extending the chain, forking the chain, extending a fork, this and that. So I'll just start kind of writing this out, and you can follow along. So first off, extends chain. If we're extending the chain, will just be if the previous ID is equal, if the newly observed block's previous ID is equal to the tip of our chain's ID, right? So -1 means end of list, and so yeah, this means that like this new block will go. We can just tack this right on the end of our chain. And so that means it's just extending. So the next condition is, we'll call it forks chain. And fork and branch are kind of interchangeable. As a verb, I think fork is a little better. As a noun, I'm kind of using branch. So yeah, I think branch is a little bit better for how we use it. So they're a little interchangeable. Hopefully you'll get this. There'll be some. It'll make sense when I use them differently. But forks chain, I think, is a good variable name. So we'll say block dot, and we'll just check. So yeah, first we want to say this variable should be not extends chain, right? And I'll explain that in a second. And so you can have this backslash to separate lines in Python. And so you can say and then separate the lines. So we're doing a conjunction of two separate conditions. And so for here, we're going to say, I'll just type it out and then explain it. So not the prettiest code, to be honest, but I think it's all right. So this condition here is it checks the block's previous ID, right, the parent, and it checks that parent exists in our chain, right? So it's like, it's building off something in our chain. That's what we're checking. And so this is just a list comprehension. It just grabs the block ID for every block in our chain. And this just says, hey, this block is in there. And this is like not scalable code. You don't want to be like eventually, if you did this on the real Bitcoin blockchain, you'd be iterating over like how many, it's like 1 million blocks or something. I forget. There's a ton of blocks. So you don't want to iterate over all that. It's like absurd. So like this is not scalable code. It wouldn't, we'd have to optimize this in real life, but it works for our demo. And so that's all it's checking is like, hey, is this building off something that's in our chain? And this is just like, hey, let's just make sure that this isn't the last, the end of our chain. So we could probably be like, like you could do something like that. I just think it's like uglier. Like this would be like, and exclude the last block or something. Like there's some syntax like that you could use. So just like, because we just want to make sure that the previous ID is in the chain, but it's not the tip, right? It's not the most recent block. So I think that's kind of confusing, and this is less confusing. It's like, let's just make sure it's not the chain, it's not the tip, and but it's somewhere else. So that kind of makes sense. And so in that case, we want to save this block to like self.branches, right? And so the next thing is I'm going to say, like down here, I'm going to say like handle handle each condition separately. So each one of these conditions we defined up here, we're just going to handle them separately in an if statement. So if extends chain, and it's a Boolean, so you just say if, and we'll say pass right here. If extends chain pass, else if, forks chain, pass, else, let's just say, let's just raise an exception saying like, I don't know how to deal with that. And eventually this will become the case where like, hey, unknown block, you know, alarm bells sounding, unknown block, let's re-enter initial block download. So that's what this will become. So like, hey, I couldn't locate the parent. That would probably be, let's say that. Couldn't locate parent block, right? Couldn't find the parent, so don't know how to plug it in. So like raise the alarms and let's do initial block download again. So like we might be out of date, so let's try it. So yeah, this is just like some structure to our code. It's not like there's really no new functionality there. And we're going to need to the next thing we're going to want to do is move this validate block up here, and And so do you kind of remember when I was going through these slides, I said like, you know, you can't really validate, like for example, you can't really validate whether these are valid spends at this point, right? Because you don't know what the state of the UTXO database is here when you're over here, right? Before you've done your reorg, you can't really say like, is every transaction here spending a valid UTXO? Because you'd have to have like gone backwards and gone forwards in order to determine that. And so what that means is we're going to have two levels of block validation. Basically, by default, like when we're adding stuff to branches, we're going to validate the sort of basics, just check that it's like formed right. Like, is the proof of work there, right? We always want to check that. Like, was it actually mined? But we're not going to be able to check like, hey, does each transaction contained in the block spend a valid UTXO? We can't do that unless we go and do a reorg, and you know, doing a reorg and back every single time we get a block on a branch wouldn't really work so well. So what that means is that here we're going to want to have like two levels of validation, and we're going to do that with we're going to add a flag here called validate TXNs. And we're going to say validate transactions if we're extending the chain. That makes sense? So this flag does not exist yet, but we're going to add it to validate block. And what we're going to do is like, if this is passed in as true, so only if we're extending the chain, then we're going to actually go through and check all the transactions. And so this is all code that is down here. So I'm just going to copy this code and move it up into validate block. So like we used to run it all the time, right? We used to run it every time. Now we don't want to run it every time. We only want to run it when we're extending the chain. So that's what we're doing here. We're gonna say sorry, validate. We'll just say, all right, in the solution file I have it as false, so I'll just like a default value of false. I don't know if it would probably make sense to require it, but like this is a nitpicking thing. It's not worth to figure out exactly what the right API or calling convention for some of this stuff is. And so what we want here is if validate. So if we want to validate the transactions, then we'll do the Coinbase validation, right? And then we'll call actual validate transaction on all of the non-Coinbase transactions to see if they are valid spends, right? So, and so yeah, what we accomplished there was the ability to conditionally validate transactions. And because we're going to be sometimes extending forks, and we're going to be sometimes creating forks and this and that, we want to be able to do this conditionally because it only makes sense to validate all of these like spends if we're extending the chain. And so one other thing you'll notice is that all of a sudden this line becomes not really useful anymore, right? So we shouldn't always assert that we're extending the chain. That's what this assertion is. It's saying, hey, the block's previous ID is the end of the chain. Well, that's only true in this case, right? It's not true in this case anymore. But we still want to have a function where we can check the proof of work. And I mean, ideally, we'd add some more checks here. But I just have one for now. It's just checking the proof of work. But we should probably add more. Like here is where you'd want, if we want to do difficulty adjustment, here's probably where we want to check that the difficulty is where it should be, for example, right? Like check that the proof actually was based on the right difficulty level, something like that. So here, let's just delete that line. And now our validate block method is complete. And so we can run down here. Actually, I'm just going to delete this. It looks ugly to me. So we're going to run down here and let's kind of look at the rest of this stuff. So given that the function body of handle block is basically like, this function is becoming like a router. It like, when we get blocks of different types that require different sort of actions, basically what this is doing is it's going to route them to the correct function that can handle that sort of new block, right? And so this sort of stuff like doesn't really fit in. And again, this isn't always called. We won't update the UTXO set and we won't update self.blocks in the case of forks chain, for example. So these no longer belong in this method. They should have a method of their own. So I'm going to delete that and make a new method called connect block. What's going on here? So I might have a syntax error somewhere. Like usually when you, I don't know, like when the indentation starts to get weird, there's usually a syntax error somewhere. Vim is that smart. It's kind of dumb, but it's at least that smart. And just because for some reason I did this in the solution file, I'm going to revert the order of these two, just stick this one first. And let's say if they're all good, update like see this comment had like code in it, and I think sometimes if you're going to have comments, you should use like the English. You shouldn't like put a bunch of variables in your comments. It's like the purpose of a comment is to sort of like give you another perspective on what's going on. So using English I think is generally better because that's the whole point of a comment. And so next, as I said earlier, this update UTXO set is it's sort of not the best function name, and because it also, if you remember, it also does stuff to the mempool. So it's like, you know, that's sort of like, it should say that in the function name too, maybe, if you're going to go this way. So what I propose is basically we're going to say connect means like basically play this block, like accept it. Now that I think of it, maybe like accept block would be a better function name. Oh, I hate it when this happens. This always happens when I'm recording this stuff. It's like I'll get to the recording part and I have it all set up, and I think of like a better name. It's like, oh shit. So we'll just say, I think accept block is probably better, but let's just call it connect block, and then we'll call it connect TX, right? So instead of update UTXO set, we're going to call that connect TX. And so let's look everywhere that we do it. So we do it in mine Genesis blocks. Let's call that connect TX, and then we have the function name. So it's kind of nice. The one nice thing about calling it connect though is that you have a reverse, but we can eventually make a disconnect method. And so accept, there's not like a negative for accept. See, it's so hard to name things. Like, it's just so hard. So I'll let you into my thoughts a little bit there. So we now have a new function name we now have a new function name that's a little better, and just to get a little bit of, so let's see here. So we can kind of delete some of these lines, and we still want to do block propagation because basically, like, if we didn't raise an exception by this point, we probably want to tell our peers about it. And so so here, this is like, this comment is no longer any good, right? Like check work. Well, we don't check chain ordering. It's like not really very good. So I'll say always validate, but only I'll just say TXNs. Always validate, but only validate. Oh, this is what I have in the little solution file, and so it kind of helps me if I keep things exactly the same. So always validate, but only validate transactions if extending the chain. So you don't have to type all these comments like I do, but I do think it kind of helps to have like well commented code. And so now we sort of like scaffolded this method, and the only thing we need to do is fill these things in. So so just think for a second, what should we put here? And maybe pause the video. Like, what should we? I would actually say pause the video and try to figure out what to put in these two spots. Both of them are like one line, pretty simple. So this first one is just, we're going to call connect block, right? We just copy and pasted the code. We just pasted the code to a different place, and we renamed it connect block. So we'll just say self dot, right? And then I'm just going to do a little logging. It's hard to get that right. I think I got that right though. No, that's not right. Yeah, there we go. That looks good. So extended chain to height, len of self dot blocks -1. Remember, because like height indexes from 0, so that's why we're subtracting 1. And so now we have this one, and so I'm assuming if you wanted to try it, you'd pause already. And so with this one, we're just going to say self.branches.append of. So we're going to create a new block, which is like a list. It's a list of blocks, and this one's just only going to have this one block in it. So we're just going to create a new baby chain with just one little block in it, and this block plugs into our main chain. And so let's copy this logger thing, and let's say created branch, and then let's say like the number of the branch. So what we'll want is, instead of len of self.blocks, we'll say len of branches -1. Actually, we don't even need the -1 in there. I think it's a little bit better. So branch number 1 would be like the first branch you created. Branch number 2, branch number 3. This doesn't have to be exact, it's just comments, but I think it's good to make your code kind of precise. So, so on that note, let's go and try to run the test again. So I'm not going to run this one function. Actually, well, yeah, I'm not going to run this. I'm just going to run them all. And so looky there. You have 2 passed, 5 failed. And so I don't really know how to get PyTest to tell you exactly which ones. Like, I want to have an output where it just tells me which ones passed or which ones failed. But you'll notice test fork chain and test fork chain and test extend chain were not like, don't show up here. Those were the 2 that passed. And so we have two passing tests. Yippee, hallelujah. And so I just want to show you just a little bit, like this is where we're at. POW coin underscore 3. This is how far we've gotten. So like if you want to compare what we've done with yours, it's a little different. I may go and edit some of the stuff. You can see as I go, I sort of edit some stuff and I make mistakes. So for example, this logger.info of block accepted, that actually doesn't make sense anymore, because like what block accepted where in a branch on the chain, like that's all of a sudden ambiguous. So let's kill that. And so for example, couldn't locate parent block is what we're logging now. This is what the solution file has, couldn't handle block. That's actually kind of crappy. I think I should go through and change that. And the logging, it created branch and then give it a number. I think that it makes sense to index from 1 there. Like the first branch would be number 1. The second branch would be number 2. This would have been indexing from 0, probably just because I copy and pasted this line up here. So, it makes some mistakes and I update it as I go. I think these are some better, these are nice comments, so I'll probably leave those in there. But yes, this is where we're at, and so this is what you should be checking your code against. And so for the next section, if you want to check your code in the next section, if you want to check your code against what we're working towards, you'd be doing POWCoin underscore 4. Once you get to the point where you got this working, then it's POWCoin underscore 4. Now that we have 2 tests passing, let's figure out what to do next. So you can see these 2 tests: test extend chain, test fork chain. These were the 2 that were passing. And I think I want to attack the next 2, these 2, test extending fork and test forking fork. This one's kind of like an edge case, but while we're here, we might as well do it. It's really not that hard. And so yeah, let's go ahead and try to get these 2 passing. Try to I'll just go through this one. So Bob mines the Genesis block, and then he mines a block on top of it, right? So this third parameter is what block is like his base, and then he mines another block on top of that. So those are heights 0, 1, and 2. And so Alice comes along and she mines a block on top of the Genesis block, so that's height 1, right? So that will create a branch, and then it's not going to do it's not supposed to be a reorg or anything. It's just a branch of length 1, and then she'll go and mine another block on top of that, right? So she specifies node.branches of 0. Sorry, this is like wrapping lines here. So node.branches would just be a list with 1 block in it, and so 0 will be that block. And so she's just going to mine on top of that. And so what we'd like to happen is that node.branches would just, the first element in the first branch, node.branches of 0, would go from a length 1 to a length 2. This block she mined will be stuck on top of that. And so that's what we're going to check. We're going to check, after she mines it, we're going to check that there's still 3 blocks in the main chain. There's still only 1 branch, right? We only created 1 branch because the second, she mined on top of her branch, so she should just like extend the branch, right? So, oops, Twitter. So if you recall over here, like this is where we're at. Like, so this would be the Genesis block. Bob mined 2 on top of it, and so Alice goes and mines 1. And then she mines another one. She should be here. It should only be 1 branch. It should not be 2 branches. It's just 1. And then we check that that first branch, right, node.branches of 0, has 2 blocks in it. And so that's a sufficient test. We're not, we could test more, but that's going to be the first test. And then so the other one is like, let's say, so this is kind of So this one's going to look like this. So, Bob will go and do the same thing he always does, mines 3 blocks. So Bob, this is Genesis block, and then 1, 2, and so that's kind of the starting position. And then Alice will go and mine 1 block, and then she'll go mine another one on top of it, and then she'll go mine a third one on top of that. So it'll be like a branch up and off the screen here. So you'll basically need to like the way we're going to store that is instead of having like like since she's going to go off of this, we're basically going to create a new branch that is this block plus the new one she created. That's kind of... So the case we're handling here is, Bob will go 2 blocks and Alice will mine 1 and then a second, so she'll extend the chain, so we're like kind of repeating what we did last time. And then she'll go mine another one on top of this. And so the way we're going to keep track of it is we're just going to, we're going to make a new branch that has this block in it and then one other block that is sort of like, it's different than this one. She'll mine 2 different blocks that are the same, that have the same parent. And so this isn't something, usually you'd have different people doing this, but this is just like a hack to make our, just test our code works. And so yeah, so you'll see she goes and mines a Genesis block, then mines on top of that, right? She mines on top of, so you'll see Alice goes and, Bob will mine a Genesis and 2 more. Alice will mine on top of the Genesis block, see over here. And then she'll go mine on top of the first block in her branch, and she'll go do that again. And so the way we're doing it, so the way we're making it so that the two blocks don't conflict is you'll see, I mean, this is kind of like, I'll just, oops. So where do we want here? So you'll see when I go full screen here, we pass in this other parameter nonce. And so what nonce does is it just, it's like this is, it's as one line, it's like this, it's too long, so I'm wrapping it here. I should probably be wrapping like sooner because the, whatever. So nonce means like start at the nonce, start at this nonce. Remember the nonce was like the magic number that made the hash of the block low. So this is just saying, hey, start at that one, and basically skip the first good nonce that you find. So it's like, when she was mining it here, she had that nonce, so we're going to just start at that nonce plus 1, so it's going to guarantee we find a second nonce. And you'll see in mine block up here, we take in nonce. We just usually start it at 0, but if we pass in a real nonce, that goes in here when we create the block. That's like where our mine block will start the nonce at. So yeah, this is kind of how it's going to work. And all we do here is we're just going to assert that after doing this, we'll end up with 2 branches. They'll both start with this first block she created that was off the Genesis block, and then the first of these 2 branches will have this one as the second item, and the second branch will have this one as the second item. So just kind of look over that. I think it makes sense. What we're doing, this is like, there's many different ways we could store these branches. We could have some like, on the one extreme, we could like keep a complete copy of the chain for every branch, right? So that would be kind of inefficient because we're storing everything so many times. We could also store every block only once and then have another data structure that just sort of links them all together, or like have a function that goes through and links them all together or something. But this way is pretty simple. It's whenever we're having a fork of a fork, we just go and copy all the blocks that were before the fork point, and yeah, so it'll make sense when we go through the code. Okay, so I'm going to split the screen again and hop over here to our my POWCoin. And so I'm going to run down to handle block again. You can hit ZT and Vim to pull it to the top for you Vim freaks out there. And so what we're going to want to do is we're going to want to create a few more conditions. We're going to want to create an extends branch condition and a forks branch condition. So That the extends branch will correspond to this one here. I call it extending fork. I'm just going to leave that. Actually, let's just go ahead. I'm just going to. So this will probably already be renamed. Just for consistency's sake, I'm going to call this. I'm going to use the same terms. So yeah, this will probably be updated when you run the code, so you won't have to make that change. But so over here we're going to have those two, and then when we handle the conditions separately, we'll add more clauses for each of these. So and you can just do ... is the same as pass. It's like no, do nothing. But it kind of looks better. It means like, fill this in, buddy. Okay, and so this is kind of where we're going to want to go. And so the first thing we need to do is we need a method to find blocks in branches, right? When we get this block here, we got to be able to like basically iterate through all of our branches in some way to figure out if it's in there, figure out where it is, and so I'm gonna go right up here, and I'm gonna write such a function. So what it's gonna do is it's going to do two for loops. The first for loop is going to iterate over each branch. It's going to consider branch 1, branch 2 until we run out of branches. The second for loop is going to iterate through each block in that branch, right? So for a given branch, we're going to look at every block, and we're basically just going to see, hey, does it match this one, right? Or we'll be able to say like, hey, does it match this one, or hey, does it match the previous block of this one? Because sometimes we're looking for like when we're calling find block, we'll either want to look for the previous block, the parent, or we'll be wanting to look for this block itself. La-di-da-di-da. La-di-da-di-da. Okay, now that we've got two tests passing, let's make another two pass. So you'll recall that last time we got this test extend chain to pass, the most basic case that our code already handled previously, and we got test fork chain to pass. That's where we got a block that built off a block built off a block on our chain, but was not the tip of our chain. So we had to move it into a branch, and we just saved that as just a list, right? Remember, we just saved that as a list with just that block in it. So it's basically like the complete list of things that are in that branch that are not in our main chain. And so if you look at the next test, I think this one and the one below it are the two we're going to attack next. So this one is when we're extending a fork or a branch. So this is when, if we hop back over here, let's say here we are, this is a couple blocks back, these two have been observed, and then all of a sudden this one shows up, right? It builds off a block that's not in the chain. That was the test. That was this one up here. That was this test that would create this initial branch. And then when we see this block, then we don't create a new branch, we extend this existing branch, okay? And so that's what we're going to test here. We're going to test the extension of branches. And so what happens is Bob mines 3 blocks. Alice mines atop Bob's Genesis block. You can see here on this third parameter. She mines his first block, which is his Genesis block. And then she mines another one on top of the first item in the first branch. You can see it wraps around, the lines wrap a little here. So it's the first item in the first branch. So she's just mining atop this. It would probably be easier to just pass in these Alice block, and I'm a little inconsistent with that, but this video's taken long enough, I'm shipping it. And then so we make some assertions, and so what should happen here is that there should be a block, or there should be a branch with both of these blocks in it, with 2 blocks in it. Yeah, and I'm a little sloppy here. I name them both the same thing. Oh well. But we see here, after doing this operation, the main chain has 3 blocks in it. The branches, there's only one branch, and the first branch has 2 blocks in it. So that means that in all likelihood these 2 went into that branch, and you can tell that that's kind of the case because Alice has no balance, right? You can see here Alice has no balance, so none of these blocks she mined, she's not getting credit for those Coinbases. And then so the following test is a little trickier. This is when basically it's the same as this test. We do exactly the same stuff, but then here we do this step twice. We mine 2 blocks on top of the block at height 1. Okay, so you'll see here, Alice mines 2 separate blocks, right? And so what we want to have happen is we don't want these to go into the actual main chain. We don't want them to create a new branch. Excuse me. We don't want them to extend the normal branch. We want them to create another branch. So we're going to want 2 branches after this one, and so that's sort of the, you can kind of read through this. It's the same thing until right here. And so what we do is we mine a second block, and you'll see it's kind of, the line formatting is kind of goofy, but if you view this file full screen, it'll look a little better. But we just take the nonce that we got in the first block she mined, second, and we add 1 to that, and we start mining at that nonce. So this guarantees we're going to get 2 distinct blocks. We're going to get two distinct nonces, so the hashes will be different, even though the blocks themselves will have all the same data inside. And that's just how we do that as a hack. If you just look up into the definition of that code, well, I might as well just do it. So mine block, you see it has a nonce. We normally set nonce to 0. But if we don't, it'll get passed in here to the creation of the block, and then when we actually mine that, that's where the mining will, the nonce will start when we mine it, increment the nonce up to something where the hash of the block is low. So just a little review on what a nonce is for mining wise, and so yeah, this is kind of an ugly thing, but that's basically this is the only new thing we do. And what we're wanting to check is that we end up with 2 branches, right? The first one has her first block and then the second block. The second one has her first block and then the third block, right? So the first one is this one, this one, and this one. And the second one is this one and this one, right? Because they both mine on top of this one. And so that's kind of the ordering. And just like last time, we don't have nothing new has happened to the main chain. These balances are exactly the same as in last time, and probably in the one before it, I think. Yeah, we only mine 2 blocks here, so it's not exactly the same. But the Alice has gotten no credit for mining any of these blocks she's mined because they haven't made it the main chain on this node, and so yeah, that's pretty straightforward. I mean, once again, you don't have to like completely understand what's going on in these test cases. They're partially for my benefit. So when you guys have inevitable problems, I can more easily debug your code. So yeah, if these are like slightly confusing, that's okay. A lot of this is just so that you guys don't come to me and say, hey man, I turn on Docker and nothing happens. Like debug my code over Google Hangouts, like that's not fun for me. So yeah, this is what we're going to try to implement. So if we hop over here, basically we're going to need a few more of these conditions, right? And so I'm going to make some. So extends and ... means like do nothing. It's just pass. Rich is attentive as always. So then we got forks branch, and we'll fill that in later. So forks branch means we had a branch and someone mined atop one of the middle blocks in that branch, not the end. And then we're going to want to make a couple new kind of handlers for these different conditions. And so the question becomes, how can we determine well, what's the right condition here? How can we recognize someone is extending one of our branches? How can we recognize someone is forking one of our branches? And basically, we need a general purpose function that can look at this block's previous ID, block.prevID, and say, where is that in our branches? Is it in one of the branches? Is it not in one of the branches? And if it's in a branch, at what height is it in that branch? Is it in the middle? Is it at the beginning? In which cases that would be a fork, right? Because it's failing to extend. But if it's at the end, if it's the end of our chain, then it needs to be this case, right? So it's basically we're doing the same thing here, but we're doing it in the case that they're in branches. And so what I'm going to propose, since this is like slightly more complicated, since we have more than one, we can't really just do a little one-liner like this. We have more than one possible. Since we have multiple branches, I'm going to make a function for this. And so the way I'd want it to work is I'm just going to show you how I'd want to be able to call this function first. So I'm going to say. I'm just going to say just underscore for now, and I'm going to fill that in what I want to name it, what I want to name the return value. So I want to say self.findInBranch of block.prevID. That kind of makes sense? And so for this side, I want to actually have it extract a few variables. I want to have it return a few variables. And you can do that by returning a tuple and unpacking them is the keyword here if you want to Google something. Unpacking the variables like this. Okay, so branch would be the full branch where we found it. Branch index would be the index in the list of branches. And then height would be the height of this prevID block that we found in the branch that we found it in. Okay, I'm going to make a little comment here. Look up the previous block. I'll just say previous block because that's how I have it in my notes here. And so we got to write this sucker. So I'm going to do it right above here. And so the way this function is going to work, let me just write out the definition, the name. So it's going to take a block ID as its one and only parameter, as its one and only function argument. And so what we're going to want to do here is we're going to want to iterate over all of the branches. And then for each branch, we're going to iterate over every block in that branch and check if that block's ID is equal to the argument block ID. Pretty simple. And then what we're going to do is we're going to return a tuple. We're going to return 3 separate things so that we can unpack them when we call the function. So I'm going to just start writing it out, and we're going to use the enumerate keyword here. If you recall, when you iterate, you usually just get the items that you're iterating over. If you use the enumerate function, the built-in function, you're able to enumerate over the index and the item. So if you don't remember enumerate, just Google it. But it's going to allow us to pull out this branch index and height as we iterate and return it all when we find a match. So I'm just gonna type this out. So we're gonna write the outermost for loop iterating over the branches first. Okay, so pretty simple. We iterate over the branches, getting the branch each time, and then with enumerate, the first one becomes the branch index, right? And that's what we're gonna want to be able to pull out here. And then so for the second for loop, so remember a branch is just a list of blocks. We can iterate over that, and the heights, the indexes are the heights. Starting from 0, these are the heights. And then we do our condition. If block.id is equal to block_id, we're going to want to return these, right? So that's kind of a nifty programming thing you can do, is you can return a couple pieces of information, and as long as you remember to, you know, when you call it, you remember to unpack them in the right order, everything works. But, you know, sometimes if there's a bug in your code, maybe it's that you got these in the wrong order. That's kind of the gotcha here, and one of the risks of using this technique. But I think all in all, it's better. And so we need to handle the case that we can't find this block. And so what we're going to want to do is we're not just going to let it return none, because actually none would blow up if it got here, right? Because we'd be trying to unpack none, and you can't do that. You need some sort of iterable to unpack it. So we want none, none, none. And so when there are commas like this is like implicitly a tuple. So like you see how it 1, 2, 3, it's the tuple 1, 2, 3. So that's what we're doing here. It's just a little bit more. This is like a stylistic thing. A lot of times people in this context, they won't use the actual parentheses here. It looks a little cleaner this way. And so now that we have these pretty little parameters, and we have a function that can get them, let's fill them in down here. So extends branch will basically be if we found a branch, so we can say branch and. So you can do like, this will take the Boolean value of this when you and a couple things. It'll just check if it's there or not. And so if branch is not none, right, which it would be if we don't find anything. If it's not none, this will be true. And so we're going to say true and. Then we want to check that the height is basically the that the height we found was the tip of this branch, the end of this branch. And to do that, we just say height minus 1. Length of branch minus 1, because the length of branch, right, will just return how many are in there. But we index heights from 0, right? So this is like an indexing from 0 thing, which programming is so often like, so many of your errors are like indexing from 1 or 0. It gets to be a pain in the ass, but I think it's better, like height means index from 0. That's what it means in Bitcoin. So we're going to be consistent there. And then forks branch would basically mean we found it in the branch, right? So branch and, but then height was anything else. It was not the end of the branch. It was maybe the middle or the one before the end or the first one, anything else. So we'll say height does not equal length of branch minus 1, right? So that just like covers everything else. So you'll see like these are logically pretty similar, right? Like it's just checking if it's the last one, and this one's basically checking also if it's the last in the branch. This is checking, hey, is the previous ID the last in the chain? And this one's saying, hey, is the previous ID the last in the branch? And these two are pretty similar, right? This one up here is like, hey, is it one of the other ones in the chain besides the last one? And this one is, hey, is it one of the other ones in the branch besides the last one, right? And if I were a little bit better programmer and didn't have so many things on my plate, I'd find a way to make this a little cleaner code. But hey, the class will, someday I'll record all these videos and they'll be perfect, and you know, Satoshi will come down and smile upon me, or he'll smile upon me from heaven or something. I don't think he'll be probably done with Earth, but that's neither here nor there. And so now that we have these conditions defined, let's write the kind of the handler code to utilize them. So first off, let's do extends branch. So think for a second. What do you think extends branch will do? Hint, hint. It basically it's in the variable name here. Try to figure out. Just pause the video for a second and try to figure out what both of these would be. Like, you know, given like, so this is kind of the answer for this one, or that's a hint for this one, and you can look up to this one to guess what this one would be. So you can just kind of pause the video and try to guess what I'm going to put in here. Okay, so now that you've paused the video, as I'm sure you have, good students, I'll show you the answer. So branch, we're going to take the branch, and then we're just going to append the block to it. Right? Extends branch. You know, append, extend basically mean the same thing, right? So branch.append just extend. So we had let's say we had a 1 block branch up here. You know, we had a 1 block branch. We got another one, then we made it a 2 block branch. And so forks branch, what we're going to do, this one's a little trickier. We're going to say, let's say, so we're going to say we're going to append to it, and we're going to append. We're going to make do a list comprehension here, or we're going to not a list comprehension. We're going to say branch of all the blocks up to and including this parent block. So the way you do that is like this. So you'd say branch, and then we do a slice, and then we go up to height plus 1. Because height is like the height. If we did colon height, that would stop right before this this parent block. But we want to include the parent block, so we're going to say height plus 1, and then we're gonna add to it the list branch. So it's not the cleanest code, but I think it actually is pretty straightforward. So like, just take everything in the branch up to and including the parent, and add, not branch, excuse me. And so for this one, we're going to say self dot. And so for this one, we're going to create a new branch. We're going to say self.branches.append. So instead of like appending to a branch, we're going to create a new branch and append it to all of our branches. And so what we're going to do here is we're going to take everything in the branch that where we found the parent, up to and including the parent, the block with prev ID, and then we're going to cut off everything after that, and we're going to tack on this block we just observed. So let me show you how to do that. Okay, so it's pretty concise here. I don't know if this is good code or bad code, hard to tell, but I think it's pretty straightforward. So what we do is we do a slice on the, excuse me. Sorry, this should be Brent. And so for forks branch, we want to create a new branch. So we're going to say self.branches.append. And what we're going to do here is we're going to take everything from the branch where we found the parent block up to and including the parent block, but excluding everything after that. So we're going to do a slice on the branch. And then after that parent ID, or after that parent block, we're going to add this block that we just observed and have a new list that will be appended to the branches. So this is how it'll look. So it's hard to say if this is good or bad code. I think it's all right. We do a slice. Remember, this is the slice operator when you put a colon inside the brackets after a list or something that you can iterate on. And so we say up to and including height plus 1, because height would stop just before the parent block. Remember, height is basically the index in the list, the index in branch where we found a block with this ID. So we want to include that, right? Because that's the parent block of this one. So we want to have a full chain. So we're going to end our slice at height plus 1, right? Because remember, like, let me just remind you, so list of range of 10, 0 to 9, right? So if we do list of range of 10, if we go up to the 10th item, or up to the 9th item, right? So so this would be index 0, 1, 2. If we go up to 9, it's only gonna it basically stops there, right? So if you wanna catch the 9th item, you got to do 9 plus 1, right? And so that's what we're doing here. We're just saying, like, because the slice operator will stop 1 short, we have to add 1 to it. Hopefully that makes sense. And so yeah, I think those two logically are correct. And so now I want to write some logging while we're here. And so okay, sorry about that line break again, the wrapping around the line. But so now we're using this branch index because it's nice in the log to know which branch we're to see, like how many branches we've created. So we're going to use this branch index variable we created up here, and we're going to say we extended it to, and then we're going to like the height. So we're not going to say height, the word height, but this is implicitly height. So it's the length of the branch minus 1, right? Because height or length will, like, again, because height's index from 0. And then here we can just sort of like copy this because a lot of it's going to be the same. And so delete up until the parentheses here, just like anything inside the quote, and we'll say created. So created branch, and then length of branches minus 1. Okay, so kind of ugly there, but hopefully that is valid syntax and everything. And I think we should add a space there, and I think here we need actually I'll just yeah, I'm forgetting a couple, forgetting that, and forgetting the same thing here. Okay, created branch to height. So branch number and then to height, and we'll say height here too. What the hell? So cool. We're now using we're using all these variables we created. We're logging every time we do something to the chain in one of the 4 cases. And so one other thing I just noticed it's not important with the logs to get this accurate, but we should, to be consistent, we should have -1 here as well, just because we're indexing from 0. So disregard that, disregard that, disregard that. And so there's one more thing I want to make a note of here. Like right here is where we have to check for reorgs in the future. This is where our hook is going to be for reorgs. So I'm gonna put a big fix me here. Fix me. Fix me. Reorg if this branch now has more work than the main chain. Basically, if it got longer than the main chain, now it's time to reorg, right? Like this is where we have to make this check. Hey, did we, basically did this happen, right? Like if we're here, we don't have to reorg, right? This is extending a branch, right? But if we're here, then we need to reorg. We just got a new best chain, and we have to go backwards. We basically have to undo these and do these. So we're not going to implement that quite yet. That's kind of the next thing we're going to do. But I'm just going to make a big fix me note. Hey, that's where the reorg's got to happen. Okay, so now that we have the code written, let's hop back over to our terminal here and run the test. So I've left my virtual environment, and I got to get back into the POWCoin directory. And so now let's run all the tests. So remember last time 2 tests passed. Let's see how many passed this time. Boom! 4 tests passed. Only 3 failed. And so now that we've made that change, let's run the test again and see what happens. So this is better now. We're getting like assertion errors, like which should be the error in a test. Like you should be asserting and something is not working. And these are all things: test unsuccessful reorg, test successful reorg, test duplicate, are things that should be failing because we haven't handled these cases yet. But we're still 3 of 4, and we're not getting like weird errors inside the code. And just while we're at it, you see how we're going to be doing these object comparisons. There's something we haven't done yet, which it feels like I've done before. Maybe it's just because I've like refactored this code so much. While we're at it, we should really add a dunder EQ method here. So this just checks if the two are equal. And so we're just going to say, we should probably like make sure, maybe, you know, if you wanted to be really, you know, you'd make sure that the other object that it's being compared to is a block object. But this is good enough. We're on our code, we're not going to be needing that. And so I think that some places in the test we might we'll want this. Usually we're comparing the exact same object in memory. So like if you don't do that, yeah. I won't explain how that works if you fail to do the EQ. I think I've kind of explained it before, but we just want this dunder EQ, and just like we have it on the transactions here. And so yeah, that's just something we're going to want to have, and it's easy to add. So let's just add it now, and with that, we're ready to move on to sort of the next section here. So if you look in the code, or if you look on the file system. So we're basically the exact same thing. Like, I made a couple little edits, but yeah, what the fuck? Feels like I've defined this 50 times. Yeah, it does feel like I've defined that a lot of times, but I don't know. So I guess I didn't. So yeah, that's where we are. POWCoin underscore 4. If you're stuck, that's where we're at. For the next section, we'll be going to POWCoin underscore 5. So if you want to like cheat a little bit and look at the next section, if something's not working, that's sort of your cheat file. And so now the one we're going to be doing is we're going to be doing, wait, what did I do? Okay, so handle block on the left, on the right side, on the left side, we're going to go to this test duplicate. This is the first one, and it would maybe make sense if I moved it. This is where it is, test duplicate. So basically what this happens is so basically what we do here is we mine a block, and inside mine block, you'll remember that you probably won't remember, I'll remind you, sorry. Node.handle block is called inside of that. So it'll actually run handle block. And the reason we do this is I just don't want to have to be calling my handle block every damn time we mine a block. I want this to like do a couple things for me. So to mine and to handle. So maybe I should call it mine and handle block now that I think about it, but won't change that either. It's good enough. So what we're going to do is we're going to go then call handle block again, even though we've already handled it, right? So here will be a duplicate block. And if you recall, where was it in these slides? So yeah, remember there were these 6 conditions. You see 5, reject blocks we've seen before, reject duplicates. That's what we're going to do with now. So this test just says like, hey, if we've already handled it before in our main chain, it should cause an exception. It should raise an exception. And then so what we do here is we mine. And so what we do here is we mine the same block again, but with Alice's node, and this will just give us a different ID. So this will become a branch, and so we assert that we have it in a branch, and then what we're going to do is we're going to have that same block get handled again, even though we already have it in a branch. And so this is another duplicate. It's not a duplicate in the chain; it's a duplicate in a branch. And so if we've already seen a block before, we don't want to see it again. We already got the sucker. We don't need it anymore. So this should raise an error too. So we're saying if we've seen the block. Again, these are like, this code is kind of messy. If we've seen the block in the chain or in a branch, reject, cause an exception. And so let's go and implement that. So I'm going to just stick this this is like logically kind of like the first, like we don't want to be calculating all these things if we've already if we already know, like it's kind of logically the first thing we should check. So let's just say like ignore if we've already seen it. And so I'm going to have a found in chain variable. Damn, underscore key is so hard to find sometimes. Oh man. So and then we're going to check if either one of them's true. Found in chain or found in branch. If we found it anywhere, let's blow up. Right? If found in chain or found in branch, raise exception of we'll just say duplicate block. Let's say that. Receive duplicate block. And we don't, like, there's just no use. We already got it, right? We already got it. So I just want to say, like, an exercise to the reader, try to fill these in. Hint, one of them will use find in branch. So try to do that. Try to see if you can fill these in. So now that you've tried, hopefully you have tried by now. If not, pause the video. But if you have, so I'm gonna fill it in. So this one would be if block in self dot blocks. All right, if we've seen this block, and this is one of the places where we want that dunder EQ. We want this because the in operator actually checks. When you say like a in list, it'll go through everything in the list and say, is this thing equal to A? Is that thing equal to A? So this is one of the places we need to be able to have object comparisons. So that's a good thing we got that. And so yeah, block in self.blocks, right? If it's in self.blocks, that means we can find it in the chain. We located it in the chain. And if we found it in a branch, we can say so we're calling it with block.id this time, not block.prev_id, right? Here we're looking for the parent because we're trying to figure out where to place this sucker. At this point, we have a new block. We have something we haven't seen before. Here we're trying to say, hey, do we even, is this old news? We want to, if somebody's telling us an old block, and we'll get a lot of old blocks because every time basically every block, we'll basically get it more than once because if every time our peers hear about it, they'll tell us, if they found it helpful, they'll tell us, even if we were the ones to tell them. So we'll get a lot of blocks twice. So it's just, we'll just reject them. And so, and then here we'll just remember this returns a tuple. So let's just pick off the first thing here and say, we'll just pick off the first thing in the tuple. So this would be branch, and we'll just check if it's not none. Because if you recall, if we can't find it, it'll return none, none, none. And so we'll just pick off the first one and check if it's none. And so now that we have that, we should be able to, this next test should pass. So, praise the Lord, praise God, pray to God here. I'm not a religious man, but whenever I run unit tests, I become very religious. So yeah, you'll see now we have two tests. Remember last time we had two failing? So here all of a sudden test duplicate is no longer found. And as you recall, what was it called exactly? Test duplicate. If you recall, if you put the double colon here and then the test name, we can just run that one and it passes. So there we go. We got another test passing. Our code is really improving very rapidly. Our handle block is now kind of becoming sophisticated, where it was just like a really naive thing that could only hack it onto the end of the chain if the stars aligned. And so it's becoming sort of a little bit more intelligent now. And so if we hop over here, you'll now see that we're basically at POWCoin _5. We have a couple little, like this was something I thought we needed, but we didn't need. Like this won't, I'll update these files before you see them, but this is what I'm following along with. As you'll see, like at the top here, I basically describe in this doc string. I describe all the new things we did. I forget if I mentioned this or not. But so we'll say handle block ignores blocks we've already seen, right? That was the one change we made here. And so again, this is the kind of solution file. And if you look, good God Almighty, so we went POWCoin 1, 2, 3, 4, 5, and actually POWCoin underscore final I'm going to delete. So now we're actually at POWCoin, the final one here. This is the next one. So let's get into that. This one, we're going to fix this one line of code, reorg if we need to. So this is, let's hop into this. And so you'll see here we got this error. It says probably an object with a faulty repr. And repr, if you recall, is the method that tells a Python object how to print itself. And so it says none type is not subscriptable. And so if you look up a little bit farther here, this will show you actually, so I think this, I don't know if these are the same. Yeah, I guess this is the stack trace, the actual error. And so the problem is we were trying to say, we were trying to read off the first 10 digits of a prev ID when the prev ID is none, and that's how it is for the Genesis block. So when we added the Genesis block, this kind of broke our way of printing blocks for just the Genesis block, and we didn't see it because we haven't been printing the Genesis block, right? So we're gonna have to do a one-line little fix to make it so that doesn't blow up anymore when we try to print the Genesis block. But you see, this is sort of something that like you only see when you run a test. And so, and this one is test duplicate, we haven't handled that yet. So test unsuccessful reorg and test successful reorg and test unsuccessful reorg actually both fail. So, and so that's kind of what we'd want it to be. So let's just hop back over here and look for the repr on block. And as you'll see, prev ID will be none for the Genesis block. So what we got to do here is, I'm going to delete that and put it up there, and we'll just call it prev ID, and then we'll just make what should we say? We'll just say none, and because you can print a none. So this is just gonna prevent us from doing this slice on something that has that is none, right? Because this is basically what we're doing. This is basically what we're doing. None type object is not subscriptable, right? That's the same thing we're getting here. None type object is not subscriptable. So this is what we're doing. None of first 10. Oops. So bugs happen. I'm sorry. Okay, so for implementing reorgs, this is going to be our playground right here, this line 243. So I'm going to delete this comment, and let's make a couple lines here, because this is where we're going to be doing our business. So this is kind of how it's going to look. We're going to say we need to check if we have a new longest chain, right? That was the comment. That was the reorg if this branch has more work than the main chain, right? So that's what we have to, we need a condition to see if we've got a new longest chain. And so this condition is only relevant in this particular case, so we're going to have the code inside the if statement, because it just doesn't, if we're in this code, this, you know, we don't want to have the condition like out here. We want it in here because it only is relevant if we're extending branches. So this is basically what we want to have. We want to have like we want to grab our main chain, basically like the blocks on our main chain since the fork, right? Since this branch forked off. That makes sense? And so then we can compare whether the branch or the blocks on our main chain has more work in it, right? Because everything before that Everything before the fork block is the same, so we don't really need to compare that. We just need to check, since there was a fork, which guy has more work, right? And if this guy's got more work, we need to reorg. If this guy's got more work, then we just leave it alone, because our current best chain, our previous best chain is still the best chain. And so what this is going to look like is, once we can calculate that variable, and we'll do that later, we'll say if total work, and total work is a function we're going to need to define, if total work of the branch is greater than total work of, if total work of branch is greater than total work of chain sense fork, right? If the branch has more work than the chain sense the fork, we'll say we'll log something here, logging.info, and let's say reorging to branch, and we'll once again use this branch index that we got here when we looked it up, when we looked up the prev ID in our branches, right? So this tuple unpacking business is actually coming in quite handy, wouldn't you say? We were able to use these variables, especially in logging, you know. So sometimes pulling out a little bit more information can be nice, because it's now convenient for logging, you know. So instead of having to do, like, you know, every time we have it, we could have to say, like, you know, branch.index of, sorry, like, you know, we could say, how do you spell branches? Is it with an ES? I've been staring at this. So yeah, I think that's how you spell branches, isn't it? Yeah, self.branches. Yeah, staring at this so long, I forget how to spell shit. So, so yeah, you know, like, we could have to type this out every time, look it up. But since we grabbed out the variable, we can just use it every time. So I think that's quite a bit better. So it's just a little kind of a programming note, you know, how to program well. I'm still learning. You know, you never really figure out how to program well. You program like a little better than you used to all the time, but there's always all these things you don't really know how to do right. So once, if this is true, if our branch has more work than our main chain, then this is what we're going to do. We're going to say self.reorg. And here I'll put some question marks, because I don't know what it's going to take as a variable. And so I'll just fill this in right below this function. We're going to make a reorg method. And we'll put some question marks, just because we don't know what arguments it's going to take. And we'll put an ellipses there as just like a pass, a do nothing. And so this isn't, yeah, I mean, this is a syntax error, so it's not really that helpful that this is not a syntax error, but oh well. So, and so what self.reorg will do at a high level is it'll go march backwards through all these chain sense fork blocks and basically reverse their effects on the mempool and the UTXO set. And then once it completes those, and once it basically is at the fork block, then it will go and start connecting all of the transactions in here, calling connect_tx, and also validating them, right? It'll validate them, and in particular, it'll validate the, you know, it'll validate each block, and it'll validate the block with the validate_transactions equals to true, because we're going to want to check whether every spend is valid, right? Because now our like these are, we're extending the tip, we're extending the chain, so we want to make sure we pass that in as true, and that's what we get once, if we can get all the way to the end of this list, then this branch was completely valid, and we will get this method will exit, and now we will have a new chain, and basically this branch, these blocks would now be preserved in self.branches. Basically, we don't need that anymore. We'd save these in self.branches as, like, you know, because then maybe two blocks are mined here really quick, and now we have to do the same thing in reverse and go back to the, you know, the fork we had originally. So yeah, that's kind of at a high level, and I'm going to explain it over and over again because these reargs confuse the shit out of me. So I'm just going to try to over explain this. And so let's make one other comment here. Let's say, oh, actually, no, sorry. We want to keep that. Sorry, I thought this was the one I was, yeah, we want to keep that. We want to keep that one, sorry. And so let's make a little comment here. Reorg if branch now has more work than main chain. And so now before writing out the reorg method, let's fill out this variable. So what we're going to say is we're going to want, before this, we're going to want a fork height. We're going to want to calculate the height of the fork so that we can basically just grab those blocks off of self.blocks off of our main chain. So here goes nothing. So actually I'll write it backwards like I usually do. So self.blocks of fork height. So what this means is we're going to start at the block at the height after the fork. So fork height, and we're going to go one after that because we don't actually want to. We don't want to include the block where the fork happened. We don't need it actually. So we'll only include the stuff where we're only going to include the parts of the two chains that disagree, right? Because the fork block is their last agreed block, so we can ignore that. So we'll go from the fork and everything after it. That's what this. When you put the colon at the end of the slice, that means like start here and go forever. Go till the end, not forever. Go to the end. And so fork height here is not defined. So let's define that. And it's gonna refer to a variable chain IDs. This is a little messy. I couldn't think of a better way to do this, and so this is it's slightly messy, but who cares? So we're gonna make a list of all of the IDs in our chain. Maybe, yeah, chain IDs is fine. And so you can call .index like here. If you go over here and say Python, let's move it up to the top. Say Python and like say range of. Actually, I don't know. Does range have an index? Yeah, so it's at index 5, right? That's what you'd expect. So you have this .index method that you can find at what index is this item in a list. So chain IDs .index of, and then we want branch of 0 .prev ID. And so this just says like let's look for the previous ID of the first block in the branch, right? So prev ID here, branch of 0 .prev ID is the ID of the fork block, the block in the chain in our main chain that the fork originated on, right? So if you remember, it'd be like this block, right? So branch would be like this, right? Branch of 0 would be like this, and then branch of 0 .prev ID would be this block's ID, right? So we're going to be like what we're doing here. What we're doing here is we're just like lopping off just these blue blocks, so we can compare the blue with the green and see which one's longer, basically. And eventually, once we have difficulty adjustment, we'll see which one has more work. But for now, it's just which one's longer. And we still have to define that in total work, which we haven't written either. So branch of 0 .prev ID. So all that makes sense. And chain IDs isn't defined yet. So chain IDs will be pretty simple. it'll just be block.id for block and self.blocks. It's just a list comprehension where you just iterate over everything and just pull out the IDs. So this is a pretty common programming idiom you'll see a lot. And so that all looks good. So now, you know, we need to add total work. And so I think, so let's hop to the top of the file, up where we have this like spend message. Actually, do we? Yeah, so we still use spend message. It's kind of weird. We should probably, this would maybe make more sense if it was on the class itself. I don't know. Oh well. There's a few things, like this is totally wrong, that I'll fix in the next version of these videos. And I'll make like some follow-on video afterwards. Like these are all the things I would change next time. And then the next time I actually will change them. But so neither here nor there. Let's write a function here. Actually, we'll just call it blocks. We'll call it chain. No, we'll call it blocks. I just like don't want to use the word chain. I don't want to say blockchain, guys. I do not want to say it. Okay, so sorry. I just don't want to say blockchain. Here I say chain. I can't say blocks IDs here, can I? I'm just looking for a way to not say chain because it's just so polluted, that word. So I think this looks good. So block chain IDs equals block.id for a block in self.blocks. Fork height is equal to chain IDs.index of basically the fork block ID. Chain sense fork is take everything in there's a bug, self.blocks from the fork height plus 1, because we don't care about the fork block. We only care about the ones after it, right? Like we don't care about the gray block here because we're only comparing the disagreeing chains. And then so if total work of branch, and you'll recall total work is just we just call length. When we do difficulty adjustment, we'll actually want to check basically, so like right now, like our difficulty bits, remember? This is hard-coded. So with difficulty adjustment, which is going to be happening in the next video, the final video in the series, with difficulty adjustment, this will be variable, and it'll actually be it'll be an attribute on the block class. Every block will have to say, hey, this is how many, this is how difficult the mining problem I solved was, and then the protocol itself will say, okay, it'll check every time, like, oh, is that a valid, is that difficulty what it should have been, right? Basically, are they cheating and mining too easy? And so so when we do that, we'll have to actually go and like do some math on and just basically add up totally how hard, basically how many bits of difficulty sort of were like how many total hashes they needed to solve this problem. So and so yeah, so that all looks pretty good. I think we're kind of ready to go here. So I'm just gonna I'm gonna delete that and so now let's actually fill in the variables we're gonna give to self.reorg. We'll give it branch and branch index. So which branch just overtook our chain and what was the index of that branch in self.branches. And so now that we have that the variables filled in the calling portion, let's fill them in the definition portion here. There we go, and now we have time to write reorg. Holy shit, we finally made it. This is kind of the, in my opinion, probably the most interesting part of the course. So let's do this. So I'm going to write some comments to just sort of like map out what we're going to do. because there's sort of 3 steps here. So what we're going to do is we're going to, starting from the tip of our current chain of self.blocks, we're going to be disconnecting blocks from our chain. And this is like what we don't know how to do, right? I sort of like, we talked about this over here, right? We have this, where was it? This, right? Well, how do we reverse block acceptance, right? How do we like go backwards, right? This was the slide here. And so, and it's also like these ideas here is like, you know, undoing what these blocks did to our UTXO set and mempool. So we're gonna have to write, just like we have connect block, we're gonna want like a disconnect block method. And actually, we're not gonna write a disconnect block because we're only gonna use this logic here, so we'll just write it here. But it's gonna do the basically disconnect blocks. And the reason why we have connect blocks as a separate method is we'll actually have 2 separate places from the code where this will be called. This will be called in normal conditions when we're adding to the chain within handle block, you know, the first case up here, and we'll also call it deep within reorg when we've gone backwards and we've reached this point. Now we need to connect this one and connect this one and connect this one. So that's why we have it defined as a separate method, because we use it kind of twice in our code in different places. And that's, in general, that's a good time when to turn some code into a new function, is if you're using it twice. Like if you're only using it in one place, unless your function's like super long and ugly, your current code is super long and ugly, you can just probably leave it where it is. And so after that, we're gonna replace the branch used to exist in self.branches at branch index, and so we're going to replace that branch with the blocks that we just disconnected here. So we're going to be like pulling them out of our chain, undoing what they did to our UTXO set and mempool, but then we're going to keep them as basically a branch and then stick them in self.branches, right? Because we want those, we want to keep a record of them in case they get, you know, further extended, and we have to reorg back to it, right? So we're going to keep track of those, and then here is where we actually will now that we've disconnected all the way back to the fork block, we did this, right? That's this first part of code. It's going to be like do this. Now we're here. Now we're going to go forward up here. And if we have any problem, like at this block, if all of a sudden we find an invalid spend, we're going to be like, uh-oh, invalid spend. I'm going to delete this block, delete everything that's after it, and we're going to go back to where we started, and this is going to just exist as a branch of length 2, because this will be gone. We'll get rid of it because it's garbage. And so yeah, that's connect branch, rollback if error encountered. So let's start writing this guy out. So since we're going to want to keep track of the blocks we disconnect, the first thing we're going to do is create a variable called disconnected blocks. And then we're going to iterate. We're going to iterate until the end of our chain is the fork block. So while self.blocks of -1, while the last block in our chain has an ID that's not equal to the previous ID of the branch, the start of our branch, right, which is the fork block. Well, until we've gotten all the way back to the fork block, we're going to basically delete the tip of our chain and undo everything it did. So block is equal to self.blocks.pop. Then we're going to iterate over the transactions in the block. And for each, and we're going to call self.disconnect_tx on each transaction. And this method has not been defined yet, so that's going to be the next thing we got to do. And so that's going to basically undo what that transaction did to the UTXO set and mempool. And then what we're going to do is we're going to add it to disconnected blocks, and we're going to add it to the beginning of the list. So like basically, how can I explain this? So when we disconnect this one, it'll go to the front of the list, and then when we disconnect this one, it will also go to the front of the list. So the result at the end will be this one is first and this one is second. So we'll always put it in the front so that we maintain ordering, because we're doing it backwards. So we have to put them on the front to maintain this ordering, so that we can just tack this on as a branch. Hopefully that makes sense. Yeah. Oops. And so that's how you stick on the front of a list, dot insert of 0, 1. So okay, so since I think this is like slightly confusing why we're putting it into the front of the list, I'm going to make a little demo. I made a little demo for you. So I made a file foo.py here. I probably won't save it to the video, so like I won't save it to the files in Git, because it's like kind of trivial. But if you want to like run through it, just copy or just pause your video and just type the code out. It's really simple. So like what we're doing here is we have like, this would be like our blocks, right? Just a list of numbers. And disconnected would be like our disconnected underscore blocks. And so we have just like, well, the last number in the list does not equal 5, right? Because 5 is kind of in the middle of numbers. We're going to pop off off the end. So maybe I glossed over that, but popping will just this will get the last one in the chain. So it'll get self.blocks of -1. And so it'll get the last item in the chain, and then we'll append it to disconnected. And so this is what will happen if we just use append. If we go to the back of the list, Python foo.py, you'll see that when you run that, you'll get numbers as 0 up to 5, and then disconnected is these, but backwards. So like in our case, we want to maintain the ordering of everything we disconnect. So a better thing to do would be to call insert with and 0 is the index we want to put it at. Insert says like asks where do you want me to put this thing, and that's the 0 is where, and what is number, the second argument. So when we do that, you'll see that the ordering of the things we disconnected is preserved. And that's what we want in our blocks, because the next thing we're going to do after we've disconnected everything and saved them in disconnected blocks, we're going to want to say self.branches of branch index. Remember, the second argument to the function is equal to, because what was stored here was branch. And we actually don't need that anymore, because we have it here as a variable, and we're going to be putting these things into our main chain. So we don't need it as a branch anymore, so we're just going to overwrite it and put disconnected blocks in there in its place. That makes sense? So we're just going to overwrite the branch, because we're basically now wiping it away, and we're saving what we just disconnected. And the whole reason why we want it in the right order is because we want to be able to we want it in the right order, so that if we ever reorg back to this, it's in the right order and we can just reorg to it. So we don't have to, it's sort of prepared and ready. And we'd reorg back to it if it was extended 2 more blocks, then we'd be reorging back to it. And so now we still have to write this method. Like, that's not defined. The rest of it is defined. So we're going to write this, but we're going to do it later. I just want to focus on this reorg method, and so you kind of see the whole picture. And then there will be this one disconnect transaction that we still have to write. But we're going to do that after we kind of write out the whole reorg method. So what we're going to do is we're going to connect the branch, meaning we're going to iterate over the blocks, and for every block, we're going to attempt to validate the block and then connect the block. And so if you remember, connect block is basically connect every transaction and update the UTXO database and the mempool accordingly. Do the thing. So let's write this out. So we're going to do a try and accept, right? And so the way this is like attempt to do this. If you encounter something bad, we can do something. And so the reason why this is important is because we say rollback if error encountered, right? So if at any one of these points we find like an invalid spend that we could only detect when we get this far, then we're going to, you know, like, for example, if we have a UTXO that's created here, someone spends it here, and they attempt to double spend it here, we actually would not really be able to tell that double spend attempt here is a double spend attempt, because we wouldn't know that the UTXO it's been created, or that it's spending has already been spent, because that happens in these two blocks here. That until we actually reorg and start checking them, we wouldn't know that. And we're not going to like keep multiple UTXO databases for all our branches or whatever. I actually don't even know what Bitcoin does here, how they actually implement it. But for us, we're just going to wait until we get to the reorg. And if we find something bad and nasty here, we're just going to say, okay, see ya. We're going to roll back and come back to where we started. And so I will start here with the try part. So we're going to validate the block, and then we're going to connect it. So validate block, and we're going to say validate transactions equals true, right? Like we want to actually check whether the spends are valid in the transactions. Even if you don't forget what this is, just hop up and take. Well, every time I say that, I realize I should probably go and look at it myself. So look at it with you. So remember, by default, the only thing validate block does is checks the proof of work. And if you pass in validate transactions equals true, it'll go and actually call validate Coinbase and then validate transaction on every contained transaction. That's a danger of going and looking in the reverse. I'm so jittery on my keyboard, I tend to delete things. So, okay, let's get this thing centered again. So validate block, and then validate transactions equals true, and then self.connect block of block, right? And so, yeah, that's what we would want to do for each block in the branch. And if we can do that every time, you know, that's this portion, right? So the first part of the code was this, and the third part was this. And so if there are no errors, great, we've just completed a reorg. If there were errors, what are you going to do here? You just found, we should really stress this, like, okay, we're here, right? How are you going to get back to here? Like, how are you going to do that? Are you going to write a def undo reorg function? Something like this? Just think, you know, pause the video maybe and think about what we can do here. It's kind of a bind, isn't it? Like, how do you get, we're over here, how do you get backwards? Well, I'm here to tell you, Justin's looking out for you. This reorg function is such that we can do this. Since we have our nicely ordered blocks that we disconnected, we can just say, hey, let's go and reorg back to the things we disconnected. One line can undo this whole thing for us. And we know these are good, right? Because these were in our chain to begin with. If somehow we pulled these out of our chain and they're invalid, like, game over. The whole thing's broken. So, that's pretty nice, I gotta say. And so after doing that, let's say reorg failed, and let's return, because we don't want to, once we do that, we don't want to continue trying to validate and connect blocks in this thing that was bad. And so the other cool thing you'll notice, remember I was saying how this one would get deleted? If we found an error in this one, when we're reorging back, this won't show up anymore. So like by calling reorg here, basically when we so this is like recursively kind of calling itself, right? This is recursion. This is like one level recursion. So when we call reorg with disconnected blocks as the argument, it'll get here, and self.blocks at this point, if we go back to our diagram, would just be these two blocks, because these two made it in, they were good. And so when we roll back, these two blocks will be saved as a branch. But this one won't, because it never actually got in before we called reorg on the disconnected blocks. So that's how this guy, and if there were a couple more after, that's how they get kind of excised. And so yeah, that is, I never thought we'd get this far. We have the whole reorg method written except for disconnect transaction. And lucky for us, disconnect transaction is basically just the complete opposite of connect transaction. So let's look for connect TX. And let's see. Let's put disconnect transaction right after it. So let's start writing this. Def dis. So it's just going to take a transaction as its one and only argument besides self, right? Which is it comes in every time you have a method call. And so we can just kind of like follow along with this guy up here and just basically do the opposite. So and I'll do the same thing where I kind of write out the whole thing, and there's going to be one method we need to fill in afterwards, but we'll do that at the end. So first off, we're going to want to add back UTXOs spent by this transaction. God, it's such a hard word to spell or to type. Add back UTXOs spent by this transaction, right? Because here we were removing UTXOs that were spent. So let's add them back, because like this is undoing what we did with connect transaction, right? So there were UTXOs in our UTXO set prior to this transaction. So when we disconnect it, we got to put those UTXOs back, right? Just doing the reverse. And so, of course, we only do this if it's not a Coinbase, because Coinbases did not spend UTXOs, right? And it mirrors what we have up here. And so we're going to do this for every TXN, because the TXNs are sort of like where the spending of UTXOs is sort of like specified. And so TX in to TX out is not defined at the moment. That's what we're going to have to define. So this will just, given a TX in, it'll go find the TX out that was was spent by this TX in. And now that we have that, right, we're adding back UTXOs. So the first thing we do is we look it up. We find out the information, right? And so and now that we have it, let's add it back in. Right, and so this will look exactly the same as this, right? See, we're just adding a UTXO to our UTXO set, and so that's how that looks. And so yeah, and where we were deleting it before, now we're adding it, right? Where we added it before, next, now we're going to have to go delete that. So So remove UTXOs that were created by this transaction, kind of the reverse. Right here, we were saving them, saving the UTXOs that were created. So again, doing the reverse. Move this up in the middle of the screen a bit. And so we'll iterate over the TX outs, because we're going to be removing them from the UTXO set. Del self.utxo set of txout.outPoint, right? And so you'll see this line is exactly the same as well, it's roughly the same as this line, because the txout and txin both have an out point. There's some small amount of goofiness here, like this isn't, when I redo this I'll change this slightly, but yeah, no, don't need it. Yeah. And so lastly, we want to put this transaction back in the mempool. And so if tx not in self.mempool and not tx.is Coinbase, right? Because if it's already in the mempool, well, let's not add it again, right? Because it's a list, so you can add things twice to the mempool. I used to have it as a set, a Python set, and the nice thing with a Python set is you never have to do this check, because you can add the same thing to a set twice and it only shows up once. But I took that out just because I didn't want to confuse you guys with sets. I think that's probably a good idea. It's better to just use the simple data structures, I think, for something like this. And so we also want to check that it's not a Coinbase, right? Because, well, Coinbases should never be in the mempool, right? That's like spend free money, right? So if this is true, let's just append it to the mempool. And let's log that we did that. I don't know if this log is strictly necessary, but I think it's kind of nice to do that, because it's like, if you're testing around and you, yeah, it's just kind of nice to see that it got back to the mempool. So yeah, now this function is mostly complete. We just need to write the txin to txout method, and we're going to do that at the top of the file again, along with total work. And so this function is a little goofy. It's the funniest looking function we're going to write in this class probably, but just follow along and tolerate all these for loops, okay? Right, so it took txin and then blocks. So we'll say blocks. And then we'll say for block in blocks for tx in block.txns. So this kind of, and then we're going to check, is the transaction ID equivalent to the txin.tx_ID? Right? That was one of the properties of txin. It says this is the transaction that spent me, or that this is the transaction I'm spending, right? And this is the index in that transaction I'm spending. Just gonna check, hey, if is this the transaction they spent? Or if is the output they spent contained in this transaction? That's a better way to say it. And so if it's contained in the transaction, then this is where to find it. It's in that index in the outputs. So we just look up the transaction at that index in the outputs of the transaction. And then we're just going to return and so we can actually just return this. So we'll have grabbed the TX out that we're looking for. TX nuts. That's not what we want. It's TX outs, not TX nuts. That's hilarious. And so now that we have that, we can pretty much let's look at disconnect transaction here. And so now we have this set up. We grab out the TX out, and we stick it in the UTXO set. And so yeah, the rest of this looks like I'm trying to sort of like spot bugs. It would be a miracle. It would be a true Christmas miracle if I could run this code and have it work the first time, because you've seen that usually doesn't happen, and if it happened here, that would truly be a marvel. And so there's one more thing we really need. Actually, let's go back to our terminal and try to run our PyTests. My God. 7 passed, 7 collected, 7 for 7. Holy crap. Our code does reorgs. Let's see. This is too good to be true. So let's say let's go look at our Docker file. Okay, Docker file is using POWCoin. So let's stick a little my in front there. And okay, I'm going to call my shot. I'm going to say that this actually won't fully work yet, but I want to run it once first, and then I'll explain why it doesn't work. And there's one line of code we need to change. So, but I'm going to run it, and this will work basically exactly like our old code worked, but it will not. Well, actually, it'll probably be shattered pretty quickly, because now we have this disrupt. So from the beginning of the video, we had excuse me, we added disrupt, which would like sort of simulate crappy network conditions. So yeah, it's shattered, right? The network is just done. It's already got chain splits all over the place. So it's got 5 blocks. Like, it was able to do initial block download, and after 5 blocks, or after the next, basically got 1 block that was good, 2 blocks. And on 7, we had a chain split already. So yeah, I mean, everyone's just mining their own chains at this point. They've completely split. And so the problem is that we still don't have a method basically to when you miss a block, when you don't hear about a block, you never hear about it. And so remember, we went through all this trouble to make initial block download, so that like, it's not just when initial block download isn't for when you just get on the network the first time. It's for any time you fall behind. And so technically, the first time you get on the network, you have fallen behind. You're way behind. You're at block genesis, right? And so, but if you turn your computer off for a day, hey, you're behind now. You need to re-enter initial block download. If you're doing, if somebody just dropped a chain that is a couple blocks longer that they mined in secret somehow because they control, 99% of the hash power or something, that's another thing that could happen. And so, and you'd have to re-enter initial block download for that too. And stuff like that could happen if if your internet just goes out for 20 minutes. You got to re-enter initial block download. You'll hear about a block, and someone will say, "Hey," here's a block. They'll say, "I don't know about that. I'm gonna re-enter initial block download and try to catch up." So basically, here when we say couldn't locate parent block, we need to do one thing before that, and that is call self.sync. Re-enter initial block download. And so let's say, I'm going to rewrite this. Encountered block syncing. Okay. encountered block with unknown parent syncing. That's a good, nice little error message. And so, is there a, yeah, there's an empty line here. Okay. And so now we're going to run it one more time. And God willing, a Christmas miracle will happen. We will see a bunch of reorgs, and the chains will all be in sync at the end of them. So we're going to pretend, you know, so okay, here we go. Initial block down. So we got 5, 6. This is where the chain split started happening last time. And so look, we have two blocks. Okay, so what the heck happened there? So both of these guys mined a block at the same time, and neither one of them heard about it. But look, the guy says created branch. So they both sort of created each other's branch, or created a branch for the other guy's block, and they just kept going. So a bunch of chaos happened here as the next guy gets online. He's doing initial block download. But look, like, lo and behold, when all this dust settles, the 3 chains actually agree. Even though that these 2 guys mined different blocks at height 7, somehow, and I don't see where the logging happened. There should be some sort of a log, but one of these guys, so here we go. So this is probably node 0. Node 0 lost the battle. The node 1, yeah, look, so node 1 mined block 8. You see that? And so node 0 lost the battle. And so when node 0 hears about that block, he's like, okay, I'm gonna send a sync request. I'm gonna go catch up, and he goes and catches up, downloads that block, and when he hears about it, he says, okay, node 1 got a better chain than me. I'm gonna reorg to his chain, and he did. And then look, the next block, they're all in agreement. They have the same length. They haven't split. So here it happened again. There's another kind of chain split. And you'll see all over the place, since we're doing this sort of unnatural setup. And so here you are. You go to like 37 blocks down. They're still synced. And look here. Now they're still synced. They're still all on block 74, all on block 72. There's a lot of, since we're simulating like this nightmare network where like almost no, like 1 in every 10 messages disappears, and every message has like a 1 second, half a second delay on average. But even with all that simulation, look, like these guys, just one guy mined a block and the other 2 accepted it really quickly. And so like whenever somebody, it doesn't matter if you miss you miss blocks, it doesn't matter if you fall behind. You basically can go and catch up. And when you find someone with a better chain than you, even if some of your blocks are now invalid, you can rewind back to a best known spot and then play forward. So this is amazing to me. Look, oh my God, they're all in sync. It's just unbelievable. So, so yeah, you can run this for a long time, and I think it should stay in sync. And so all these logging messages we painstakingly wrote are now really interesting. So you can sort of like watch this and try to decode what's happening. And so so yeah, this is like kind of I hope you guys enjoyed this. We still have one more video to go, but that video is, in my opinion, a little less interesting than this stuff. Well, not less interesting, it's actually super interesting still, but it's a little less hard and like mind-blowing. And so let's just hop back to the slides here. And yeah, I mean, this is, I don't have much more to say. I mean, I'm sort of in awe that it even worked, even though I spent the last like month trying to make this thing work. Like, yeah, and I think the code is pretty simple. Like, we only added, so the number of lines, so WC-L is how to count lines. I could just, so we only have 640 lines. That's actually pretty good. Remember in our little advertisement I was saying it'd be like 1,000 lines? So we've actually managed to like cut out quite a bit of what I, like, we're coming in way below schedule, way below the estimate here. So that's pretty cool. And so we still have a little bit more to go with the monetary policy, but honestly that's not a lot of code change. So maybe we could get in around 700 lines. We'll be like 30% under schedule. That would be really under budget. That would be pretty cool. So So yeah, this is next time. Our monetary policy stinks. We actually kind of don't have one. Well, we do, but we don't. We haven't really thought about it all. We just mint coins forever. It would be more scarce if our terminal rate of issuance was 0, right? Like that's. I kind of buy. I mean, this is maybe you could argue, but I just kind of think that that's like the perfect monetary policy, right? Money is a ledger. It's like it's just a way to keep track of unspent productivity, right? Like you want to be able, you want to be productive, and then you basically want to defer your productivity, like the consumption of the fruits of your labor, the fruits of your productivity, until the future. That's what money is. And so it makes sense if the global money supply is just fixed, because that's, you don't want a ledger that's moving around. I think it's better. And so I sort of call this like the global inflation problem. We want to make it so in the end we have a fixed supply. And this is very attractive to potential users of our currency too. Like, this is what they want. This is what the individual wants. They want to store their unconsumed productivity in a way that it won't be destroyed. And so the second problem is that an influx of hash rate will cause inflation, right? If all of a sudden 10 times as many miners show up, we're going to get 10 times as many coins, and that's like this is like a global inflation problem, meaning like it's long-term inflation. I call this one like local inflation problem. We need a way to have the difficulty respond to rises and falls in mining participation. And so we have these two sort of inflation problems we're going to tackle in the final lesson. And so halvenings are going to be the solution to the global inflation problem, and difficulty adjustment will be a solution to the local inflation problem. And so there you go. That's the end of the video. My God. Let's go have a drink, huh? Let's go have a drink. I'm going to go have a drink. Okay, bye.